Okay. Welcome to this session. Around the neck. Yeah. Yeah. Like this? Oh, okay, okay. No, it's the other way. You want to? Oh, yeah. Anyway, welcome you all. We start this session. The first speaker is Kendrick Smith, dealing about FRB real-time software and algorithms in CHIME, CHORD, and others.
Okay, thanks everyone. My goal is to give a talk about algorithms and software without putting everyone to sleep. Let's see how it goes. I want to acknowledge a huge group of people, including on the right, I put sort of the key people that are doing like the real-time software in CHIME and now in CHORD. CHIME, I guess, needs no introduction. It's just been an incredibly successful project. At the time that we wrote the FRB search, it was the largest FRB search in the world by far, and I think that it still is in data volume. Now, I suppose now that Krakow is online, that's not true anymore. You know, the key to CHIME's success is that this philosophy of having this core with huge N for gigantic mapping speed. We find 2 or 3 FRBs per day. Combined with the Outrigger telescopes coming online now for sub-milli-arcsecond angular resolution is just like a really powerful concept. The project that we're doing now, this is sort of a teaser slide for Seth's talk later today, CHORD, is a similar philosophy, but with some complementary differences. We have larger frequency coverage, which helps with signal to noise and also enables some new science possibilities. The biggest difference is that we have dishes instead of cylinders, which is complementary in the sense that we have larger instantaneous sensitivity on a smaller part of the sky. CHORD does, whereas CHIME gets the daily cadence, the full sky monitoring, which is also very powerful, just generally speaking, for transient astronomy. And so we expect that these experiments will run simultaneously and be complementary. The main thing I want to tell you about today is like the FRB search that we're doing with software that we're doing with CHORD, which I think totally crushes the FRB search software that we wrote for CHIME, and I'm really excited about it. We've been sort of rethinking the CHORD project, sort of snowballed into like rethinking all the algorithms and software from scratch. And we're doing way better than our initial targets. We're like, sort of an order of magnitude higher. So I want to tell you about how we do that. So I'm going to try to do the first 3 points in like the first half of the talk, since I think there's some people in the audience that really think about software problems most of the time. And I want to try to kind of communicate what we're doing and what aspects of our new approach have been so successful, like in a way which is maybe like a food for thought for conversations later. So I love nerding out about GPU programming and algorithms, so I'm super happy to talk to anyone who's interested. And then I think everybody in the audience is thinking at some level about the implications of all of this algorithms and software for designing new telescopes or new surveys. So I just want to make some general comments on that. Okay, so you might think that going from CHIME to CHORD would be easy thanks to Moore's law. The correlator was built 8 years later. What's surprising is that the numbers don't actually bear this out at all. If you compare the CHORD and the CHIME correlators, the CHORD correlator has 6 times lower memory bandwidth. Total GPU memory bandwidth is often the bottleneck. If you compare flops, then CHORD is a little bit lower. If you use sort of ordinary intuitive instructions, but if you use these special tensor core instructions, then CHORD is much higher. Tensor cores are like little specialized compute units on new GPUs that do low precision matrix multiplies, like float 16. one key to performance, there's really two keys to performance. One is like minimizing memory bandwidth at all costs, and the other is figuring out how to use tensor cores, including situations where they're not really intended to be used. What's sort of complicating this comparison is that the CHORD correlator is about a factor of 4 less expensive. But even if you compare memory bandwidth per dollar or flop or ordinary non-tensor flops per dollar, you can see that Moore's law has kind of stopped. Like those numbers are pretty flat. But it's really, Moore's law always finds a way. It's just not the way you expect. We're sort of getting speedups nowadays through new kinds of instructions and new ways of writing code. Okay, so the two most important, if you want to be a GPU programmer, the two most important keys for success. First off is most of the time you'll end up on modern GPUs, you'll be memory bandwidth limited. And so what you don't want is this, where you're launching a sequence of kernels on the GPU. And each kernel is reading from global GPU memory and writing back out to GPU memory. This is kind of what naturally happens if you use a framework like CuPy or PyTorch. What you want is something like this, like one gigantic coalesced GPU megakernel, handwritten in CUDA, that reads like a tile of the array from GPU memory into a compute unit, and then does as much computation as it can, storing all temporary quantities in some scheme using like registers or GPU shared memory. And you just keep coalescing until you run out of space on the compute limit and the compute unit to hide stuff, and only then do you write the result out. And so as we've like headed down this road, it kind of led us to a weird place, like writing procedural code generators, like Python programs that produce the CUDA program. And then an even weirder place is that a big key to performance is trying to use these new tensor core operations, which are like, okay, so for example, you might try to use these instructions to speed up short FFTs. In radio astronomy, we just kind of do two things, like short FFTs and multiplying matrices. And so used all over the place. And conceptually, you would think this has to work since the FFT algorithm is a sequence of linear operations, and you can always implement linear operations with matrix multipliers. But the details are like kind of insane because you need, the tensor cores are very constrained in like where the data has to be on the GPU. And you need a huge amount of like mathematical planning to get the data into the right place at the right time. So this led us to a second weird place, which is before we write code, we write little mini papers like this, which is like they're like little pure math papers, just sort of like planning out all the details of how the data is going to move around on the GPU. Okay, a problem that I don't know how to solve is, so we're getting like incredible performance. Like most of our improvement is coming from things like this, not Moore's law improvements in hardware. But it's just gotten so weird and like hyper specialized that it takes a really long time to learn. And so like a really small number of people end up doing it and they end up being really maxed out. If you know of a way to solve that people problem, let me know. Okay, so I'll talk about beamforming a little bit. The beamforming problem is that you have some set of sky locations on the sky, and then you want to compute the intensity, the square of the electric field, like averaged over some number of time samples. Surprisingly, there's a few different ways of doing this, and like different codes may look very different. The first like fork in the road is whether you apply the beamforming weights or phases before or after squaring. The first equation, I think, is the most intuitive way of thinking about beamforming, where the inner sum beamforms the electric field, and then you square and average over time. If you expand out the square and rearrange the sums, you can write it the second way, and then recognize the inner sum over time as the visibility matrix. And so these methods are mathematically equivalent. We do the first one in CHORD. I think it's always best in the limit where the interferometer is compact. But I mentioned the second approach because if you're used to thinking about it this way, then it might look really different. Okay. And then there's this little trick. We have like a two-stage beamforming algorithm where we start by beamforming onto a regular grid of sky locations, and then resample at some non-regularly spaced grid set of target sky locations by sync interpolation. That's the same interpolation kernel that arises in like the proof of the Nyquist sampling theorem. This procedure is exact because we choose the spacing of the regular grid so that it's Nyquist sampled where instead of time and frequency being the variables, it's sky location and maximum baseline. It's just the Nyquist sampling theorem in different variables. And then because this is all done with short FFTs and matrix multiplies, it can be done very efficiently on tensor cores. So this is how we get up to like many thousands or tens of thousands of beams. Another little point I want to mention is that I just think that beamforming can be a lot more general than is what's usually done. Like by default, we choose these narrow beams that maximize forward gain. But at least in this implementation, you can replace this kernel by an arbitrary matrix. So for example, you could fatten the beam by averaging over a set of sky locations. And so we kind of think of beamforming in like a generalized way, where you can do things like form RFI nulling beams by like setting the beam to 0 at a special location like the horizon or a known RFI source, or subtracting the sky average beam. A CHIME specific idea that we might do in a CHIME upgrade is to have specialized wide beams for detecting side lobes, events in side lobes. Some of our CHIME science comes, the CHIME side lobes don't fall off that fast. So some of our science does come from side lobe events. Then I just wanted to open this idea up for exploration. So if you have other suggestions for generalized beamforming, let me know. Okay, so we have this ultra-fast beamformer. We're planning like 7,000 beams in CHORD. The scaling is excellent because the first stage is independent of the number of beams, so we could easily go much higher. Also super general. Next up is the FRB search. So I'll talk about, how much time do I have left? Okay. Maybe I'll just cut this short. I'll say that so the heart of the FRB search is this transform. The input and output are 2D arrays, where the input is intensity data indexed by frequency and time. The output data is indexed by DM and time, and each point in the output array is a sum over elements of the input array that gives you the detection significance in sigmas. When we wrote the CHIME FRB search, I thought this is the ultimate implementation and we'll never speed it up by a factor of 2. That was sort of the extent to which I thought the code was optimized. And then here's where we are in 2025. If I take the current CHIME FRB search running on this purpose-built cluster and keep the search parameters the same with the new code in progress, I'm confident that we'll be able to fit it on 2 GPU compute nodes. So we could also scale the search up to these huge numbers of beams. And so I think I'm a little behind schedule, so I won't try to get into the details, but let me just say that if diagrams like this are interesting to you, then please talk to me after the talk. Okay, finally, making all this progress on algorithms and software, like along the way, we've kind of been rethinking FRB survey and even telescope design. So I just kind of want to share some general thoughts because I think this is of like broad interest. And so one tool that has been like really incredibly helpful is using a global optimizer to test hypotheses. So the optimizer was written by Seth, who will talk about it in a few hours. This is just sort of a teaser slide. And so the way it works is that you give the optimizer a computational budget, and then you ask it to vary all search parameters in sight, time resolution, frequency resolution, number of beams, beam locations, and it trades them all off against each other to maximize whatever function corresponds to your total happiness, maybe total FRB event rate. And so one surprise that we find is that the optimizer always prefers like a huge number of overlapping beams and is willing to compromise in frequency and time resolution to achieve that. So that's why the optimizer prefers 7,000 beams in CHORD, even though it's a 500-dish compact interferometer. I'll come back to this in a minute. Another plot that we look at a lot is what I call the yield curve. So this is an expensive curve to compute. Each point on this curve is one full run of the optimizer, where you give it a computational budget, ask it how many FRBs you can detect, and then increase the budget a little bit on the x-axis and re-optimize all the parameters, get a new detection rate. And so this is sort of a bottom line plot if you're trying to like assign a total budget to the FRB backend, decide what number of computers to buy. And so what surprised me is that I kind of expected there would be some clearly defined point of diminishing returns. And that point would sort of set the compute budget. That would be the point where you have like enough compute. But what we actually see is more like a scale-free power law. And so I would speculate that, and this exponent is pretty universal. It's like usually around 0.3. And so I would speculate that like all real world FRB experiments are far from diminishing returns, and having more compute or more code optimization would produce more FRBs. Like this is definitely true in CHIME. Here's one way to think about a power law. Here are two ways of designing an FRB search. So there's a smart way where you do like a lot of work up front to figure out requirements, number of beams, and so on. You write your search code, you time it, you match those things together to decide how much money to spend on the FRB backend. And then there's a dumb way where you just use a rule of thumb that feels right. Like the search backend budget might be 5 or 10% of the telescope. And you just buy as many computers as you can and later do the best you can on code optimization. And so I'm going to claim that the dumb way is better supported by a power law than the smart way. And I don't mean to brag, but we're pioneers of the dumb way in CHIME and CHORD. We're ahead of our time. So one way to say it is that a power law doesn't have a scale. So the only like dimensionful parameter is the total budget of the total cost of the telescope. That times some dimensionless number has to set the total cost of the FRB backend. And I feel like formal arguments better than hand-waving arguments. Like imagine that I can just fungibly move money between the buying more antennas at an interferometer and increasing the cost of the FRB backend. Then my FRB detection rate is number of antennas to the 1.5, assuming you put in luminosity distribution, times the FRB backend cost to the 0.3. That was the power law we saw before. And if you solve a constrained optimization problem where the total cost is constant, then it's a few lines of algebra to show that the FRB backend cost is always 20% of the antenna cost. And the point is that it doesn't depend on the constants. It doesn't depend on how well your code is optimized or what your total budget is. And if you make different assumptions, you'll get a different number. Like if you assume that FRBs are 25% of the total science goal of the telescope, then you get more like 5% than 20%. Okay, the next frontier for FRB search is, searching to high time resolution. So here's a place where we know we're missing huge factors in signal to noise. We typically run searches at millisecond timescales, but we know that bursts can be like microseconds, and so that we know we're leaving factors of like 30 in signal to noise on the table. So I'd like to contrast with the earlier statement that the global optimizer prefers frequency time resolution. And the reason is simple. The computational cost goes as the square of the resolution, since you have to improve, you have to narrow the frequency resolution at the same time that you narrow the time resolution at a fixed DM. For assuming narrow burst, the SNR improvement goes as resolution to the 1/2. And so even though like going in this direction of parameter space, as far as from the perspective of the optimizer, increasing resolution, you have the most to gain in the long run, but it's a very flat direction. The improvement is slow. So that doesn't mean that it doesn't do it. It just means that it crowds the field with beams first and then switches to a mode of increasing time and frequency resolution. And so that's kind of the direction that we'd like to go in the future. And so there's a few different ideas that we're exploring here. There's sort of, so it's not that you can't go to high time resolution, it's just that it's expensive. And so since we've made these sort of radical improvements in our code optimization, we can make some real progress getting into that regime just by upgrading the backend. So one thing we'd like to do is a backend upgrade where we switch CHIME to the new code, have a lot more total throughput, and progress into this high time resolution regime. And then there are ideas for untargeted searches. Like you could search a narrow DM range at sky locations of previously observed pulses to look for repeats, or searching special sky locations like gravitational lenses, or the top of the frequency band where the search is cheaper since DM delays are shorter. We're really interested in this, so if you have more ideas, let me know. Another way of thinking about this is like you could try to turn a negative into a positive. So I kind of framed it as a negative, that increasing resolution is expensive, whereas the SNR increase is modest. But equivalently, you could make a positive statement that if you decrease resolution, you can get huge cost savings with modest SNR loss. And so here's just a toy example to illustrate. 10-kilometer chord. Imagine that we kept chord the same collecting area, but just scattered the dishes so that all baselines were 10 kilometers. And then like imagine that the management goes insane and gives us some requirements that look impossible. I'm going to insist that we search all the formed beams, that's 10 to the 7 beams for this instrument over the full band, while not spending any new money on computers. So this just sounds like it would never work, but you can do it this way. So I'm just going to degrade the time resolution, frequency resolution by a factor of 40. That decreases the computational cost by 40 squared, which offsets this huge number of beams. And the SNR penalty is significant, but just the point is that it's not as extreme as you would think. That SNR penalty is like a factor of 6, and the event rate is more like a factor of 16. And so with chord parameters, you'd still find like 1 FRB per day with this concept. It's not optimal resource allocation. I think 10-kilometer chord would be more expensive than 100-meter chord. And so according to the rule of thumb, you should scale up the FRB backend proportionally in cost and find more than 1 FRB per day. But it's sort of a proof of concept to show that things that look insane are actually feasible. But I did assume here that the beam forming problem can be solved. And that's more like a hard compute limit where you may just fall short. And so I did check in this example that the beamforming problem would be solvable. But beamforming is sort of a different story where we need these really fast algorithms in order to do an experiment like this. And then another type of project that I think is going to become super important in the near future are aperture arrays. This is something that I think just 5 years ago, I would have said is sort of infeasible. But imagine that you just have a huge array of dipole antennas where you're like aiming for the collecting area of CHIME with no dishes. Just here's some example parameters that I chose semi-arbitrarily. Half the frequency range of CHIME, 10 to the 4 close packed dipole antennas, and just trying to survey the entire sky with 10 to the 5 beams. With some of the algorithms that I described, I estimate that you could do this with around 100 GPUs, get an FRB discovery rate of around 20 FRBs per day. The all-sky monitoring, I think that number does not do justice to the scientific power of all-sky monitoring. Like you could see every FRB all the time, every pulsar all the time, LPTs all the time if they're present. Amazing for finding strongly lensed FRBs. The total hardware cost is probably around, I would estimate to be around $30 million if we use some of this new technology from CHORD. And the cost is compute dominated, so it should decrease with time through a combination of hardware and algorithmic improvements. So when I kind of look across the landscape of radio telescopes, there's a lot of different concepts. And this to me seems like the thing that's missing. And so if you have $30 million, there's huge opportunity lying around. There's a huge opportunity to do it now. If that's too expensive, then you can wait, according to the last bullet point. Okay. So in conclusion, CHORD is coming online soon. Seth will tell you about it later today. And it'll be an amazing complement to CHIME. This second bullet point has a typo. This should be after a lot of fun. FRB beamforming and search, we're making really amazing progress. They're sort of working like 10 times more efficiently than expected. And there's some new concepts that I don't think would have been possible a few years ago, like a sparse interferometer with like 10 to the 7 beams, or aperture arrays with 10 to the 4, maybe even greater numbers of antennas. I think will be super important in the near future. Finally, I overheard some people talking about this question, whether all FRBs repeat. So to settle the issue, I asked ChatGPT, and there you have it. All FRBs repeat. So If you have any questions on that, just let me know.
Two, 3 minutes for question.
I just want to ask Sammy, but you can't hear me right now.
Shami?
Sure. Kendrick, fascinating talk. Thank you. I have a question and a comment, I guess. And my comment is more on the global optimizer that you're talking about using. My worry with that is that you are restricting yourself to the known unknown population, and that by the choice of parameters, you are potentially ruling out some unknown unknowns than a more general search would. It's a worry, but obviously, there's only so much you can do. So that's maybe a concern. I don't know how.
Oh yeah, it's like, so I totally agree with that, and I think of it as the question of what cost function you should be trying to maximize. I don't actually think that total FRB rate, as I was showing on the slide, is the right cost function. You want something that makes sure that you retain sensitivity all the way out into the corners of parameter space where events are rare but super interesting. So like a specific cost function that I like better is you just kind of like identify, you put a candidate FRB at each corner of the parameter space and maximize like the sum of the log of the event rates. That doesn't require a population model since it's independent of the ratio of event rates. And sort of ensures that a 10% improvement in any corner of parameter space has the same value as any other corner of parameter space or in the middle of the parameter space. But yeah, we spent a lot of time sort of brainstorming cost functions because it's like not obvious what the best choice is.
Right. And then a quick follow-up, your beamforming, it sounded like it was actually very straightforward to beamform on a uniform grid, and then you had additional steps to sort of steer the beams to different positions. Is that an argument to just use uniform beamforming and call it a day?
Yeah, for compact interferometers, I think so, but for sparse interferometers, I would do it differently. There's some technical points here that really make this idea work. That being able to do the short FFTs with tensor cores, and then just formulating interpolation as matrix multiplication. Yeah, like this algorithm is this way of doing it is really fast on modern GPUs because all of the important steps can be done with tensor cores.
Question on that?
Yeah. Hello, I'm Albert from University of Toronto. Thank you, Kendrick, for all this great introduction to the cost optimization of a radio array. And I'm really interested in the huge dipole antenna array that comes possibly in future. May I ask, so in current architecture like CHORD, the antenna cost is dominated by the antenna itself. But when we build thousands or millions of dipole antenna, will the cost of each antenna become dominated by the electronics and the digitizer? And how is there any possible way to tackle that to drive the cost down to an acceptable level? Thank you.
Oh yeah, so you shouldn't take my cost too seriously. I'm quoted $30 million. And so here I was assuming that the costs were going to be like dominated by the compute. The point is it can be done on 100 GPUs, and 5 years ago I would have said that it takes thousands. I don't think I answered your question.
For example, for now, sorry, so for now, when we are digitizing each antenna, the digitizer itself, the F engine costs us like a few $1,000, I guess. But when we increase the number of antenna themselves, then the cost of the FPGA will soon dominate over the smaller antenna.
Oh yeah, so I'm sort of assuming that the digitization is of the same order as the GPU.
Oh. Thank you.
I'm sorry, we have to stop here.
Thanks everyone for questions. Please feel free to chat with me.
Thanks again. There will be the next session about the future where many of the questions, which I imagine the people here have in mind could be risen again. For the time being, we move to the next speaker, which is speaking about result from a pilot survey for second-time-scale radio transients with the CHIME telescope.
Hello, I'm audible? Yeah, okay. It's going to be hard to match Kendrick's talk now. I really wish I wouldn't have followed him. Anyway, so yeah, I'm Sujay. I'm a postdoc at Raman Research Institute, and I'll be talking about this new backend which you're working on the CHIME. So most of this work was also done with my previous position in TIFR, which Sriharsh, and it was his idea mostly. And then, of course, there are a lot of other people involved, which are mentioned here, and then also a lot of other people from CHIME for the collaboration. So yeah, I would like to thank, a lot of efforts have been gone over the last few years. So first thing, why do we want to search for second duration transients? Well, the answer is simple, to remind ourselves that the life is full of ironies. Before you think this guy had something for other than coffee in the morning, no, but I happened to talk to Sriharsh. I happened to talk to Sriharsh yesterday in the evening, and he said he had this idea because he looked at this source and like saw that, okay, maybe we should search for longer duration transients because it was only detected in the peak, and then there are the 3-second search, and now what is log? So it's like a weird this thing that like it's come back to you. So, but okay, coming back to some science again. Basically, like we want to look at transients because there are like highly scattered FRBs, long period transients, and then there is of course theories by a lot of people, including Navin here, that there are a lot like theoretical predictions that you have a long duration gamma, like a slightly wider duration burst from gamma ray, like radio coherent burst from some gamma ray burst or direct neutron star mergers. So, but as Ziggy's pointed out in his talk, that the CHIME FRB sensitivity reduces a bit and the wider duration transients. So, so to compensate for that, we started doing this. Basically, it was most Sriharsh's idea and I implemented when I joined. And so the idea initial was to look for transients between 16 millisecond to 5 seconds pulse width. It was to picky bang on the other search, which is also happening at the CHIME site, which is the CHAMS, like looking for longer durations pulsars, like slow pulsars. And now I think Jeff, as will mention next talk, that we will actually be able to do a parallel search also compared to the initial idea. And this will be the largest systematic survey when we are fully online. So roughly following the part here in the orange circle, or the orange yellow rectangle for it in this space diagram. So the idea was to have the pipeline very simple, based on the like well-tested routines, and also to be using just to also test how the RFI environment at these timescales would be. So what I want to point out here is that, just not going to details, is that we search for 16 milliseconds, 128 and 512 milliseconds data. And then we use Presto, we use SDV scan and fetch to do this this search. So if you want to talk to details, you can catch me in the coffee break. So the data which we had was again as a part of the CHAMS data which they collected for their search as part of their testing back in 2022, 2023. So it was in a lot of data, so we had to ship this back to India, and that took some time. Actually, you had to put it on the hard drives and get it back. And we had an instantaneous sky factor of about, so it's like a 1/16th of the CHIME sky, total available sky. And so we detect that in that one new FRB and 8 bursts from R117. So the detected FRB, which looks to be a non-repeater, at least at the moment, that it was also detected by CHIME in CHIME FRB in the side lobes. But in in the slow search, in the pilot survey, we have it in the main beam. So we have a full, it's a broadband burst, as I show. But in the CHIME FRB, you'll see only in the two other beams. So it's like in the upper half or lower half of the frequency band based on this thing. So the other bursts were out of the 8 bursts from R117, 6 were also detected by CHIME FRB, but we found 2 new which were missed by the CHIME FRB pipeline, which showing that our pipeline was doing something good there. So this is the waterfaller for all the 9 bursts. The one in red are the R117 bursts which were not detected by CHIME FRB, and the one here in the blue is the non-repeater. You can see it's fully a broadband, but as I mentioned in the CHIME FRB, it was just in the side lobe, so it was lost out. So what we did, of course, is to find the burst properties and get an estimate on all-sky rate. So this is so we took this data and which fitted with, of course, with the fit burst, and to get the basic parameters is just the one plot for one burst. So since we had 6 common bursts between CHIME slow and CHIME FRB, we were able to also, because this data is slightly different, so I had to write a few of my own routines to actually get this proper, like the fluxes, fluences, and fit burst, working on that. But we were able to cross calibrate and get that, like verify the properties of at least our analysis is at the moment working like with the 6 bursts. So with this, like just to quickly go through that, all the 8 bursts of R117 has FWHM width between 13 to 43 milliseconds, fluence between 24 to 46 milliseconds, and the non-repeater has about a width of 42 milliseconds and fluence of 19 milliseconds. So they essentially sit in this kind of you see the common part between CHIME FRB and CHIME slow. We don't have anything on the wide side. We hope to have it soon. 5 minutes, okay. So last thing we do is this with this data from the pilot survey is that look at and rate all-sky estimate, just to get what an idea about this kind of rate of this kind of burst would be. So the rate typically depends, like you'll have to compute on, assume a fiducial model, get your exposure of your telescope, and also know the completeness of the pipeline. So exposure is a function of beam model, sensitivity, and daily observing time. I'll not get into the details of it. The completeness, as I had mentioned, because the pipeline we had already had an injection routine in when we were developing. So we did the injection in some of the test data. So it is like a plot on the right showing the detected SNR versus completeness as a function of width. This is still dominated a lot by noise. This is so you have to take a bit of pinch of salt. We will do this analysis when we go fully scan and repeat it again. So here we assume a completeness of 0.8 and to do the rate calculation. And we assume a fiducial model which is similar to what the CHIME FRB catalog has assumed in terms of the fluence distribution. And we just take a width of width dependence on some power law distribution. So we have one detection and we don't really use the R117 because as a detection because it was hyperactive at that time. So this thing. So using this, just applying the forward folding this model through the exposure and sensitivity, we are currently estimating upper limit on. So this is a preliminary last week. So just numbers might change a little bit here and there, but what our upper limit is that is about 3 to the power 310 bursts per day per sky per day above fluence of 12 Jansky millisecond at width of 16 milliseconds. So at the same time, initially, we had written proposal to the lab for the funding to put a dedicated hardware. We had got it, got the funding, and then also we were able to procure hardware last year. It's been on since last year, and of course, there is new member joined last year with Jason taking it over a lot of this, and his student Jeff and Sachin has also joined, and Jeff has been working on few months on this, getting this online. You'll hear about this in the more on this talk later in the session. So yeah, that's what want to say, and we'll just keep the summary slide and take a questions.
Time for 2 or 3
questions. Duncan.
Thanks very much for this talk. This is Dunk from WVU. I was wondering with these longer width searches, how much you have to worry about the stability of the baseline coming out of the total intensity signal or the de-dispersed time series, and how do you deal with that?
So this is yes and no at the moment. So there is some one software issue at the moment from the L1s, from the where we're tapping into data, which is causing our baseline to vary a bit. We are aware of that. So there is if you take the finest resolution available right now, this baseline seems to be fine. It's not we don't see a lot of red noise. But if you downsample at the bottom, it's a bit technical, but essentially it's we are suffering in some cases, but not if you downsample the native resolution. So we are working on the fix to that, and then we'll see actually how much the red noise affects it, because there is some issue with the code. We can talk in terms of it's a bit technical.
Thanks.
Questions?
No, they are just discussing.
Why are you using Presto for the single pulse? Oh, hello, my name is Max. I'll be a PhD student at McGill. Why is CHIME slow using Presto for the single pulse search?
Oh yeah, as I said, I mean the idea was to just start with the simple, very well tested routines. Presto has been in use for a while, and yeah, I mean as we go, we might get to something else. Right now, we just to get an idea of this. As even Duncan was talking about, how the baselines are, and also yeah.
Don't see other hand. So we can think today. The last speaker of this session is Marilyn Cruces, dealing about transients search with ALMA.
Perfect. Can you hear me well? Yes, super. Okay, so now I'll be taking you to the other extreme of the radio band. And in particular, I want you to wonder, what if we observe radio transients, our favorite radio transients, at millimeter waves? This is certainly not the standard range where we like to observe fast radio bursts, for instance, or pulsars or magnetars. And what I'm asking you now is to think in this area here. We are extremely successful at centimeter waves. We have over thousands of FRBs already discovered. If you think somewhere around the L band, you have thousands of bursts for single sources, but what happens somewhere in the middle? We know that in order to understand the origin of FRBs, we need to understand what's the emission mechanism behind. And this is why we do plenty multi-wavelength follow-ups. For instance, we do centimeter radio plus optical plus X-ray plus gamma ray, but not much somewhere here in the middle. And as of now as well, if you exclude the FRB like magnetar, we haven't been successful at detecting centimeter plus bursts at other wavelengths. Now, if you think of the emission and FRBs being something like pulsars or like magnetars, then the coherent emission mechanism behind, from the coherent mechanism behind, you would expect emission at millimeter waves. So for instance, with this sketch that I'm showing you here, for pulsars, we know that we pass from coherent emission to incoherence somewhere in the millimeter range. Now, for FRBs, what happens? As of now, we have detection somewhere from 200 megahertz, roughly, up to 6 to 8 gigahertz. We have definitely a serious problem with reporting non-detections, which as a person studying the repetition pattern is a big issue. Complaint being made. We want to know what will happen somewhere here, so much further from the centimeter wave band. By the way, here I'm also posting the paper that recently came out that we submitted with my student Constanza, who this week finished the bachelor and submitted a paper at the same time. So if you want to know more about the chromaticity of FRBs, I refer you to that paper. But that's our motivation. What happens outside of the centimeter band? Now, we don't have plenty radio telescopes that are efficient at millimeter waves if you think of time domain astronomy. So in principle, you could take telescopes like Effelsberg or GBT or VLA to 20 or 30 gigahertz, but the efficiency significantly decreases. On the other hand, you have quite sensitive instruments like ALMA, but it's an interferometer. So the science they do is they take all the different telescopes, they correlate them, and they make their beautiful UV plane images, but which is not what we want because we're mostly interested in time domain astronomy. But up to recently, ALMA was not equipped to do this type of observations, but with the boost of global VLBI and as well as the Event Horizon Telescope, this new method was developed, and this is called as the phased ALMA mode. So it first started as a mode together with a global VLBI, but then it developed into a standalone mode, which is what we have nowadays. So in this mode, what we do is to take the voltage of the different ALMA antennas and coherently combine it to make an equivalent to a larger telescope. So for instance, if we take 49 of the 12-meter antennas of ALMA, we can make an equivalent to an 84-meter dish. So definitely in this range, there is nothing more sensitive than phased ALMA. Now, for the ones that have worked with ALMA, you know that it's 50 12-meter antennas for the large array, but in reality, you need to leave one antenna behind as the reference point. So this mode became available with the lower frequency band because we study pulsars. We know there is a spectral index. So the higher we go in frequency, the less likely is that we will detect these sources. So this year, band 1 receiver became available, so between 30 to 50 gigahertz band. And then we put a proposal and we wonder, can we use this to detect pulsars, magnetars, FRBs in single pulse? So thinking of the transient nature of this, not in integrated pulse domain. But we didn't want to wait. We put a proposal, it was accepted to be observed this year, but we didn't want to wait this over a year. So we thought, okay, what can we do then in order to test whether this system will actually work for us and potentially to detect FRBs outside of the centimeter range. So it turns out there is some beautiful data from EHT, in which ALMA naturally took part of it, and that we decided to use. Now our data doesn't look as glamorous as the image of the black hole, because what we took is only the contribution from ALMA, which is just an ugly time series. But anyway, I like to show this. Sorry? We all love time series, naturally. So this work is basically what I'll be presenting you now, and it's the work done by my master students, Josefina. And the idea is, can we just phase ALMA to detect FRBs or any radio transients, long period radio transients, and so on? Now, we focus in the Galactic Center because we had the data, but also it is quite interesting as a laboratory because in the Galactic Center, you have a dense environment, you have magneto-ionic environment, so you will have all the things that you have seen in some other FRBs. For instance, in this beautiful picture from Meerkat from the Galactic Center, you have a few sources there. There is definitely a missing population in the Galactic Center that is also part of our motivation, but this could be a full other discussion. But if you take a look at all the sources here, you see high RM, for most of them is also highly changing. And in particular, you have here the Galactic Center magnetar. This is the sort that is like right next to the black hole in projected distance. So because EHT people image the black hole, it turns out that the Galactic Center magnetar is lying somewhere there. This was the hypothesis, at least. And now there are benefits of going into higher frequencies, especially when you go to the Galactic Center. One of them is that you have no dispersion effect, so you can probe deeper into the Galactic Center. If you have done ever any search, you know that if you go in low frequency, for instance, there is no way you're going to reach the Galactic Center unless your source is extremely bright because your pulses are dispersed. So you can see here, for instance, the Galactic Center magnetar, when you go to S-band, the pulse is extremely broadened, but as you go higher in frequency, you start recovering the signal. Scattering as well, you are less affected by scattering if you go higher in frequency, so these two propagation effects already give you a big plus to want to go in millimeter waves to the galactic center. The elephant in the room is definitely the spectral index, which is definitely prevent us from detecting many sources in the galactic center. But anyway, there should be a tail to this distribution that we should be able to detect. So we took the data, we converted it. It wasn't easy. It was a lot of time series pieces, like 2 minutes here and there. And we were able to find, to detect 8 pulses from the galactic center magnetar. They are the ones shown here. My favorite one is for sure the brightest, which is the one there. And here I would like to highlight 2 things that I think are really relevant, because it's not just a detection of the galactic center magnetar, but what it means. We detected single pulses, single rotations of this source at 86 gigahertz, so high frequencies. And in addition, this data was not even made for us. This data was calibrated considering Sagittarius A star, which is extremely bright, not our extremely dim source with less than 50 millijansky. Now, the problem when you go to high frequencies is also that you don't have dispersion, so it's much harder when you're doing the search to distinguish whether the pulse is real or not. You don't have radio frequency interference, which is good, but because of the phasing of the ALMA system, you will have some signals, some artifacts that could look like a pulse. But in this case, in order to verify that these were actually real pulses from the source, we had polarization information. So we see that these pulses are highly linearly polarized, like up to 100%. There is circular polarization as well. We also did a bit of timing. Timing magnetars is a nightmare. I'm pretty sure people here have done it, not recommended, and for mental health. But we did it. We did it, and this part of the work of analyzing the properties of the single pulses and the polarization is work done by my other student. And what we learned, for instance, from these pulses was the gamma value when you fit there the energy distribution, and we obtained for this source minus 2.4. This is a value quoted here is 1 sigma value. So if you compare with other FRBs, what we see at centimeter waves, you see, I mean, it's consistent, but the error bar is significant. It's large because we have only 8 pulses and not many of them are as bright. But as an experiment, okay, this information can be used because now we can extrapolate if the sources in this frequency range have a similar value, like similar spectral index, how many do we expect to detect? For this frequency we were analyzing, band 3, this 90 gigahertz, we expect that roughly 100 pulsars should be detectable. So it's a large fraction if you want to study the emission properties there and to distinguish when emission goes from coherent to incoherent. And now extrapolating these to lower frequencies, so to ALMA band 1 that became available this year, we expect to detect at least 200 sources. Regarding FRBs, in the paper, we also report some analysis there, and long story short, we need more FRBs in the southern hemisphere, but repeaters especially. Pulsars, definitely, we have many, and you can see there, the larger the circle, the less time we need to integrate. But repeater and highly active repeaters are very few. So the future prospects of this work, this April, we observed the magnetar and many radiolab magnetars with band 1. So we are waiting for the data, waiting for it to be added, correlated. And for the next cycle, we expect to have the first FRB monitoring campaign if everything goes well, everything is accepted. Because for instance, for 121102, we expect the source to be highly active during that time period, if the activity window indeed applies. So just to wrap everything up, we expect that this work is just the tip of the iceberg, and we expect that many more gets motivated to do observations in the millimeter band. If you have FRBs or pulsars, magnetars, or long period transients that you think could be interesting to observe at millimeter waves, so contact me. Thank you.
Questions? This time is real.
Hi, thank you for the interesting talk. This is Adam Dong from NRAO. My question is, again, coming back to the RFI or whatever the RFI equivalent for ALMA is. It seems to me that for a magnetar or for a pulsar, you can phase connect and then you can identify. It's a real thing. It's astrophysical. But for FRB, you don't know where it's coming from. So is it true to assert that the only way you'll know it's real, because I've read quite a few core Liu's papers who just, he can't tell whether something's real sometimes. Is it true to assert that the only way to know it's real is if you had low frequency and high frequency observations at simultaneously, and then you detect them on low and high, and then so you, is there any other way to determine whether an FRB is real?
Yeah, definitely one of the most straightforward ways to know, okay, this pulse is real or not, is that you do the centimeter plus millimeter campaign, which is what we did in April this year. But in principle, because you have polarization information, so then you could basically hold this and to say, okay, this source must be real. I would say that definitely there will be a bias there, because if the pulse is not polarized, then you might not have a way to detect it. So definitely observing at millimeter waves, pulsars or magnetars is much easier than FRBs. But the idea will be combined campaigns.
Also, I think satellites can be polarized, right?
In principle, I think,
yeah.
But this is much easier to track, for instance, because you know the orbit. For instance, at ALMA, we know when a satellite will pass, and sometimes when it's too bright, we will shut the system. So this is much easier to track, I would say.
Yeah. Can you do fast? Oh, sorry. Talk to you later. Go ahead.
Hi, Kyo Masui, MIT. One of the innovative ideas that made a huge difference in the FRB field was the ASCAP incoherent sum survey. Have you thought of doing incoherent sum searches? So that you'd lose a factor of 7 in sensitivity, but you gain a factor of thousands in field of view, which could change you from being a follow-up instrument survey to a discovery survey. Now, there you'd really like a transient buffer. I'm sure it's probably impossible to install one, but nonetheless, you could still try this just to see if there's anything there to look at.
I mean, I would say definitely what we're doing now is mostly monitoring known sources, because for doing a survey, first of all, you need a lot of time. Contrary, for instance, when you observe at centimeter bands, you usually add like a 10 or 20% overhead. When you observe with ALMA, it's like a factor of 2 or 3. So definitely doing like all sky survey is not really an option now. But for ALMA 2040 or like beyond the ultra wideband sensitivity upgrade, we are looking into having ALMA as a time domain instrument. So for that, something like that could be considered. Yeah.
I guess I would say incoherent sum, the correlation cost is free. So making that commensal is not crazy, right? So anytime ALMA is observing, just tap off the voltages, square them, sum them, stream them to Mark 7 or whatever your recorder is. That'd be a very it doesn't matter where you point, right?
But we are actually discussing something like that, but the main problem is that as of now, the system how it's made, in order to phase or sum the signal from the antennas, you need solutions based on the weather and stability. So that's quite local. So in principle, you cannot just take the voltages and eventually record it. It will be less of a problem for lower frequencies, definitely.
Oh, even for an incoherent sum where you don't care about phase at all, you just throw away phase?
But anyway, the idea will be to sum the signal of the different antennas, right? So
with no phase information.
Yeah, but you need to combine the sequence. So
the ASCAP incoherent sum does not do interferometry. It does. So you take a factor of root and antenna. So you take a factor of 7 in sensitivity, but you gain the full field of view.
Okay, I mean, we could discuss this definitely.
I think the issue there could be being sure that what you see is really real, because if you don't know that there is something, it's even more difficult answering what was said.
If you see things there, maybe you can't verify them when you discover them, but you know that there's something to look for, and that that there's a future campaign, motivates future campaigns.
You could also think of, for instance, image searches. This could also.
Okay, thank you. There is not any more time, sorry. Thanks again, all the speakers of this session. And we will reconvene in half an hour.
Also,
Yeah, you got it. I'll share right away.
No, yeah.
All right, everybody. We're about to start into our next session, which is a continuation on future directions. So you're going to hear about some more upcoming telescopes, upcoming surveys. To lead this off, we're going to hear from Gregg Hallinan, who is attending remotely. So Gregg, whenever you're ready, take it away.
All right, thank you very much. Can you hear me all okay there?
Yeah, we can hear you well.
Excellent, great. All right, thanks for running a great conference, and thanks for also allowing so many of us to be joining remotely. I really wish I could be there. It's been fun to watch from here. And I'm going to talk about the DSA 2000 and provide a little bit of commentary towards the end about next steps for large-scale projects. First, I want to really acknowledge that this is a large team, and here's some of the leadership team that are involved. And I want to also mention that there are a lot of staff at the Owens Valley Radio Observatory and postdocs and students that are involved across this project. A lot of them are in the room there. Casey Law is leading our post-processing for the project. Liam Connor is very involved in our design for FRBs. And of course, we've got students and postdocs. We've got Stella and Miles and Jacob and Krithi in the room too. So please reach out to them. It's a very large project, much larger in scale than, for example, DSA 110 was. And it's been really exciting to watch it grow. All right, what is it? Well, it's actually now a misnomer because what I'm going to give some details on today is we've actually made some design changes over the last year. The DSA 2000 is actually going to be 1,650 dishes, each of 6.15 meter diameter. And we made that decision because, you know, as we got very far along in the design for the antenna, which is very stringent in requirements for the radio camera, we realized that we could accommodate a larger aperture, and that allowed us to sort of rebalance the array a little bit. It means we have the same survey speed as before, so you don't have to change your calculations that much. We will be about 25% more sensitive than previously anticipated. We operate in a single frequency band in a very radio quiet valley in Nevada and Spring Valley, and we are highly optimized for surveys. Another likely modification that we're not going to go into detail on today is we will likely also have a low band component to the array spanning 15 to about 300 megahertz. The array is made possible by two breakthrough technologies. It's the first radio camera, and really there's actually two new generations of digital backend that I'll talk through, as well as an uncooled antenna receiver combination. I want to give a big shout out to Schmidt Sciences who fund the project. They've a really unique approach to how to do big projects, and it's allowed us to go through our timeline in a very accelerated way. So just to give you that high level picture overview, I'm not sure how well the video will play there. I'm sure that it'll be a little bit choppy, but this is a zoom in on our remote site in Eastern Nevada. And like I said, it's 1,650 antennas in a very pseudo-random configuration. Random is the key. And it's spread across that entire 16 by 20 kilometer region. It's elongated in the north-south direction because we're doing a survey and we want to have as close to circular PSF over a widest range of declination as possible. And, you know, we really see ourselves as a survey telescope in every way. I think we're very complementary to other projects, including CHORD, SKA Mid, NGVLA. And, you know, by surveying the skies, we really do provide a survey of the skies in advance of both NGVLA and SKA Mid. So we're in many ways analogous to Rubin in the optical and its potential relationship to ELT telescopes. And this decade really is the decade of large surveys. I'm including here some ground and space-based surveys, that cover a very large survey area, more than 10,000 square degrees, that in combination will transform our view of the cosmos. In most of the cases shown here, you're going to increase the known population by factors of 100 or so. And together, they, I think, will provide the background and footprint for understanding the FRB population very well. We heard a lot earlier this week about the need for photosys in the next generation. These telescopes, including the UV anchor provided by UVEX, will be very important for that. All right, we are building it in this valley called Spring Valley in Nevada. We spent 2 years doing extensive surveys throughout the Western United States. And this had the best combination of an excellent RFI environment, really good soil conditions for construction. We're going to be installing enough optical fiber to go to the moon and back. And it's also got a nearby town that's separated from the array by a mountain chain that allows us to build our control center building and bring our signals back to that location. That's the headquarters for the project. This figure that I'm showing here gives you a sense of how radio quiet it is compared to the Owens Valley, particularly in the cellular bands that we want to observe in. And it really is spectacular. And we've been doing ongoing RFI surveys there for the last 3 years, nearly continuously. This gives you a sense of where in Nevada it is. It's in the eastern part of Nevada in White Pine County. And on the left here, you can kind of get a sense of the distance to this nearby town of Ely. And like I mentioned, we're bringing about 40 terabits of data along optical fiber all the way back from our array to this Ely location where most of the big compute and the digital backend for the telescope will be located. Here is a drone video giving you a sense of how spectacular and desolate this location is. I'm sure it's not playing very smoothly there, but I hope you get a sense of just how remote this location is. As a point of reference, the Owens Valley is a smaller valley with tens of thousands of people. There are less than 100 people living in this huge valley. So we began the process to gain access to this site more than 2 years ago, submitting our pre-application to the Bureau of Land Management. It's all public land. We've been doing extensive biological and cultural surveys over the last 2 years. That includes pedestrian surveys of the entire 60,000 acres of that location. As you're seeing on the bottom here, typically it's a team of 8 or 9 architects, 8 or 9 archaeologists, and a couple of trap monitors. It's taken a very long time, but it's actually completing very shortly. And we're looking at trying to complete NEPA by hopefully mid to the third quarter of 26. I have learned a lot about things I never knew and never wanted to know, including this very beautiful bird called the sage grouse. This has been one of the reasons we have to be very careful about where we place our antennas, but the process has converged very nicely and we should be able to begin construction next year. And that means we're now in that detailed construction planning. So our beautiful ellipse now looks like this, but we actually increased the boundaries by a few kilometers to make sure we retained the resolution and PSF control that we originally envisaged. So you're talking about an optical fiber network spanning the entire area. You've got a very small complex to the west side of the array where we have the radio camera front end, which really is just what you would traditionally call the F engine, as well as pulsar timing and timing synchronization hardware. That is not manned continuously. We will include all the vehicles for maintenance there also, but our main staffing facility, like I said, would be in the town of Ely. Over the last 2 years, not just the archaeologists, but many of the team I spent a lot of time, traversing the entire location, understanding how we are going to do construction, understanding the geotechnical data, and how we're going to roll out the full array. And right now we're in that kind of phase of planning out all of the sequencing of installation of all the infrastructure, the antennas, the optical fiber, receivers, etc. All right. This is just give you a sense of our timeline. And really, it's now driven by the environmental process. Most of the design is complete for the hardware, and most of the software design, software development for the project is well scoped to kind of roll out and take place during the implementation phase when construction happens. And the goal is to start construction next year. We likely will have our final design review sometime later this year. We're waiting on scheduling constraints from our funders. And the goal is to sort of switch on the telescope in 28, complete some initial commissioning surveys, and then have our full 5-year survey commence sometime in late 28, ideally. That 5-year survey has 3 main components. We will do a cadenced all-sky survey, so covering essentially 31,000 square degrees with repeated epochs. Now, we're doing a variable depth, variable cadence survey for a number of reasons. We started off with a fixed cadence, fixed depth, but we realized very quickly that because of the way the telescope sensitivity depends on elevation, the impact of confusion noise, preference for better sampling, for example, on the galactic plane, as well as, for example, on Euclid fields, we've now changed to a variable depth, a variable cadence survey. So the cadence will vary from, or the number of epochs will vary from 4 to 12 epochs, and the spacing of those epochs will be somewhat logarithmic. And the average depth is about 500 nanojanskis, but I hope we'll get about a factor of 1.5 times better than that for some declinations, and a little bit worse than that at lower declinations. Now, 25% of the time will be spent doing pulsar timing in collaboration with Nanograv. We assume up to 200 pulsar fields with variable cadence, and that will also provide sort of an intermediate depth tier for the project. And finally, 10% of the time is envisaged for gravitational wave follow-up. We were going to do deep fields, but it turns out that we've learned from Meerkat in recent years that the confusion noise we can expect will probably limit how deep we can go, and we probably will spend that 10% on LIGO follow-up and also DDT observations of other classes of transients. Now, this just determines where the telescope is pointing. Really, we're going to do the same observations for every field. For every field, we will produce a suite of image data and fast time domain data, all commensally. That includes a continuum data set for each observation of about a microjansky. After you mosaic observations together, we will do spectral line observations for every field at 3 different tiers, including Galactic H1 at 0.2 kilometers per second, Local Universe H1 at 1.7 kilometers per second, and then out to Redshift 1 with variable resolution and velocity of 27.5 to 55 kilometers per second. We will do full Stokes IQ UV imaging also. And then, of course, as you all, I'm sure, want to hear in the room, a full field FRB search and a likely beam-formed pulsar search. All data are fully public with no proprietary period. So that's a very important point to make. Once our initial commissioning surveys are complete and we turn on the telescope for main surveys, all data will go to public dissemination via our public archive immediately, including rapid alerts for radio transients, and of course, in particular, almost immediate alerts for FRBs. And just to give you some of the numbers that will be kind of complete over 5 years, something like 1 billion radio sources with full Stokes data, a few million galaxies in H1, something like 100,000 FRBs over 5 years and 20,000 pulsars, and about 1 million slow transients. Now, the science case and the design of the telescope is sort of broader than just FRBs. Really, multi-messenger astronomy is a very important key aspect. That includes LIGO follow-up and of course, pulsar timing for Nanograv. Tracing our cosmic history via H1 is a key science driver. And time domain, including FRBs and slow transients, of course, is part of the design that really drives us. And then, in the last few years, we really defined a new key science case because we realized, that the implications and potential for the dark sector and strong gravity and fundamental physics in general was very high. You can learn all about that via our most recent science workshop, which is 2 years ago now. We'll have another one hopefully in this next year. And we've also got a community science reference document you can take a look at. I can answer questions about any science case, but I think I'm going to move on just to make sure that we're able to get to the key points for the FRB search. All right, I'm going to touch on key technology, and one of the key things here is to move from that traditional paradigm of a large dish with cryogenic cooling to a larger number of small dishes where you are cryogen free. And we've been doing this really for 12 years now. We started the DSA project in 2013. Actually, the original motivation was, scientifically at least, was the recent announcement from Thornton and al. of 4 FRBs from Parkes, and as well as that, actually, the imaging and follow-up of LIGO events That's what originally, drove us to start the project in 2013. And it's kind of scaled out from then. And the first 2 generations of science instruments have been really FRB focused, because it took us the best part of a decade to come to terms with how we would do the imaging for a much larger array. And DC2000 kind of kicked off with that in mind in 2018. And at this point in time, we've got our very first prototypes of these dishes online. We're talking about a low-cost, fully steerable, solar-powered antenna with very stringent requirements in surface accuracy and pointing. Sub-millimeter RMS, because the radio camera really cannot allow for any instrument-dependent, direction-dependent effects for calibration. Similarly, our pointing requirements are very stringent, about an arc minute. This is a picture of our now fully developed quad ridge quick cake pan feed. It's called the cake pan feed because it's made out of cake pans from a company called Fat Daddy-O. And these beautiful cryogen-free wideband LNAs that Sandy Weinreb first developed, which give us about 7 or 8 Kelvin noise temperature for DSA 110, more like 10 for the wider band DSA 2000 implementation. When we first started the project, there was no commercial solution for the very, very smooth reflector at low cost. So we developed a hydroforming implementation ourselves at the Owens Valley Radio Observatory. This is the Arvo team. We spent a lot of time and effort making that possible. We didn't build a building for it yet because we want to make sure it worked first. We've now managed to demonstrate it successfully, and we actually get well below a millimeter in RMS for this design. The receiver consists of this wideband feed, and this can be assembled by one person with, an Allen wrench in about 30 minutes, designed by Jonas Legare, and here he is assembling it. And then on the right, there's 2 bits of magic for the LNA. A company in Switzerland called Dynamics produced these beautiful HEM transistors that are designed for high frequencies. But if you can get a really good matching network, will give you amazing performance at low frequencies. And that's really what Sandy and his team have done. And more recently, it's been Kieran Scheila and Steve Payton who have led this effort to produce what is our final version of this LNA. It's all basically complete. We're looking at whether or not we should embed the LNA in the feed, but other than that, it's ready for production. We've been building the test array, the first prototypes. This is the DSA 110. To the east side of that, we've been building the first prototypes of the early antennas we want to use. And here you'll see the installation of an antenna pedestal with a vibratory hammer. And the entire process is very efficient. It's actually not very invasive, which is important from an environmental perspective. We don't use any concrete in installation of a DSA 2000 antenna. You can see it being pounded down. And we now have something like 9 antennas that are online in the valley floor. And this is actually meant to be a movie that shows the first 4 of those antennas slewing across the sky. Unfortunately, the video is not playing for some reason. Okay, since we first embarked in the development of the antenna, we actually did eventually find a commercial solution. The company MTEX Antenna GmbH in Germany took our design and did some modifications and actually came up with a really clever mechanical press solution for the reflector. And we now have test prototypes of those antennas also online at the Owens Valley Radio Observatory. So really, we've got these initial test antennas. These are all of the 5-meter version of the antenna design. We're waiting for the 6.15-meter antennas, which will come online later this year. The other major... Go ahead.
Just 2 more minutes. 2 more minutes for the talk.
Okay, got it. Okay. I'm going to jump into the radio camera, and given the time constraints, I'm going to jump down. I first just want to emphasize the real goal of the radio camera was to solve a major issue in radio astronomy, which is the data output, where we've reached a petabyte per year with the VLA. We're well beyond that with ASCAP and Meerkat. I couldn't find CHIME's numbers. I know they're very large. Now, DC2000 goes to 20 exabytes per year of visibilities. That breaks the model entirely, but it turns out it gets us into a new regime. And the reason why we store visibility data for radio telescopes is because we have to solve the inverse problem. We have to actually deconvolve data to get a true image. We're solving that inverse problem, and that usually is non-linear. It's not well suited to a deterministic back end. And that's what we've been doing with this radio camera concept, is to build the very first deterministic all end-to-end imager, such that you don't now have a dirty image that looks like this. It now looks like this. And that enables really to build a stream processing pipeline that creates images. And you know, that's now something that's fairly advanced in the project. I can't go through it in much depth here. I can take questions on it. But essentially, we have the radio camera front end, which is a traditional F engine. We bring all the data to Ely, and there we do our end-to-end cross-correlation, flag calibration, grid and image. And I'll skip this step here, and I'll emphasize we really have two digital backends. The radio camera is one, and it produces these 12.7 thousand images in time frequency every 21 minutes. We also have the chronoscope, which really is our implementation for FRBs and pulsars. It will do a full field of view search, partial band for 1 to 1,000 millisecond signal pulses up to DM of 10,000. And then simultaneously, we will pulsar search for about 4,000 beams per field. All right, I'm going to skip down here. And I want to emphasize that our model for how we would do this has completely changed in the last couple of months. We were going to build a huge data center, 140 racks, with all of our radio camera front-end hardware, as well as 5,000 GPUs and 500 servers. And then it all changed this year. And this is what I really want to emphasize for this group, because I think it's going to change radio astronomy. There's been a sea change in what NVIDIA's kind of plans are with how they scale. Traditionally they've scaled out by building servers and GPUs in servers, but now they are really focusing on scaling up single solutions with very high bandwidth, memory bandwidth, within a single rack. And these are the NVLs. This is all the NVL link. And this is the first one of these, the NVL 72 system. It is transformative for radio astronomy because, as Kendrick was kind of demonstrating, a major issue you have with working with GPUs is not the amount of flops you have. It's accessing those operations. It's throughput. And these systems have enormous memory bandwidth, memory footprint, and it's going to transform radio astronomy. We were actually at NVIDIA on Wednesday of this week. I missed one day of the conference, and I managed to get a photograph with some of these racks. I didn't get to wear Jensen's leather jacket, but we had lots of discussions, and really we're going to be building the radio camera and chronoscope using two each of the next generation LVL 144 systems, each of which has 4 exaflops in terms of operations, certainly of value to fast time domain because it's FP4, maybe FP8. And what I really want to emphasize is you get inside a single rack, 260 terabytes per second, unblocked communication between GPUs, and then into a rack, 28.8 terabytes per second. We could basically bring all the data from the DSC-2000 into a single rack. Or we've heard about the idea of doing 50,000 or 10,000, dipoles. They all come into a single rack. All right, I've only got one last slide. I want to just give you by the numbers what the DSC-2000 is. It's 1650 by 6.15 meter dishes. That's 49,000 meter square collecting area. If you want to do your calculations, this is the slide you need. SCFD at zenith 1.6 Janskys. It degrades as you move away from zenith. Spatial resolution, our field of view is about 5 degrees squared, but at the bottom of the band, it's closer to 20 degrees squared, and the FRB search will make use of the bottom part of the band. Spatial resolution is 3 arc seconds at DEC 0 for full band, but much better at higher frequencies and so on. Astrometry, about 100 milliarc seconds. And that's where, really we're able to scale from fast all-sky rate. We're talking about 25,000 FRBs per year. With commensal continuum searches for example, PRSs, maybe spectral line data to be able to search for host galaxies to high redshift. And the archive will include co-location with multiband data to facilitate rapid association and robust photoseize. All right, I'm going to stop there. I had some thoughts on next generation stuff, but I think Kendrick's already covered that sufficiently. Thank you very much.
All right, thanks for a great talk. Very exciting. Do we have questions? See, Danielle?
Hi, Greg. Daniele from Marseille, France. This is a really impressive telescope, of course, but you skipped over the challenges of searching for radio burst with an array that is not so compact. So I was wondering if you want to comment a little bit more on that part.
Yeah, let me just dwell on the slide that's of interest here. I think, you know, the numbers to focus on are on the right-hand side. It's a huge search challenge. We're looking at 6 million beams. We're using the same kind of technology as in the main radio camera, just coarser grids, different convolution kernels. And the formation of those beams presents a huge challenge. But, you know, if you take a look at the specifications of the rack scale solutions we're using for our back end, I think the resources for this are amply available to make this possible. So I know the numbers seem challenging. Every generation has that, I think, impact. But the amount of compute resources that you have and the memory bandwidth between those resources with the NVL 144 rack, I think we're in good shape for this.
Thanks, Greg. This is Jory van Leeuwen from Astron. Thanks for a great talk and running an amazing project. So you focused on how you have recently changed your thought about the backend for the chronoscope. And you mentioned a little bit the hardware, but of course, these are quite specialist machines and they need to be programmed. So how are you on the human side of things? Does this mean a different expertise you need, or does it connect to what you can already do?
So we have a pretty substantial team that are doing the development of both the radio camera and the chronoscope. What I'm describing here is the radio camera, the steps you see here. The team have been working on that for about 4 years now. And I should mention some of the people involved here. Martin Picorni leads the overall pipeline development. It's all based on Legion. You know, we do data capture and cross correlation using the tensor core correlator developed by John Romain, of course, at Astron. Our flagging algorithm is actually in-house. It's called Grid Flag. It's also implemented on a GPU now. Calibration is led by Josh Albert, and it's a direction-dependent calibration and bright source removal. Implemented on JAX, currently being tested at NVIDIA on NVIDIA GPUs. And then the gridding and summation was led by Martin Picorni using what's called HPG, which is a gridder he developed while at NRAO. The chronoscope team includes Vikram, it includes Dean Howarth, Liam Connor and others. And again, it's a variant of the core concept we have for the main radio camera. Moving from our original plan to this kind of design, I think is not going to be a huge challenge for us. We're working very closely with the folks in NVIDIA, Kate Clark in particular, and we hope to be able to test on an NVL 72 system for the end of the year. The way we're kind of scaling out, we have an MVP implementation of our pipeline where we require the end-to-end full functionality for each pipeline. The main radio camera is basically ready this month, and chronoscope is sort of, you know, another maybe 2 or 3 months. So I think we're doing okay, and I think these rack scale systems only make our lives easier rather than harder.
That's very exciting. Thanks.
All right, one more question.
Mine should be quick. How much money does one shell out for one of those racks?
So it's been a fun week of negotiation. The fun thing is, the fun thing is actually if you go to the June keynote from Jensen Huang, he actually mentions a cost for the NVL 72 system of $3 million. So, you know, we expect a cost of order about $10 million for 4 by NVL 144. So that's what the very large scale, more than 0.5 megawatt of power 4-rack solution for our digital backend looks like cost-wise, which is a small fraction of the project actually.
Great. Well, let's thank Greg again. Yeah, and any further questions you can ask on Slack. as we'll just set up our next talk. All right, for the next talk, we're going to hear from Sashabaw Niedbalski about the Galactic Radio Explorer Telescope, or G-REX. So Sash, take it away. Oh,
Thank you,
and
Rob.
once the captions are gone.
Yes.
Yes, take it away.
Right, is the mic coming through well? Good, awesome. All right, hello, I'm Sashabaw Niedbalski. I'm a fourth-year PhD candidate at Cornell University, and today I'm going to be giving a status update on the Galactic Radio Explorer instrument, or G-REX for short. The goal of G-REX is all of the sky all of the time, meaning we want to be getting as much of the available 4 pi steradians of sky instantaneously as we can, 24/7. And this is mainly with the intent of when the next high-energy galactic radio burst event like SGR 1935 happens, we don't want to miss it. So there are currently 5 G-REX stations up and running. You can see them over here. They're the blue X's on the map, and then I've got some pictures of each individual terminal and the respective location of them. The red X's are representing prospective forthcoming terminals, hopefully in the near future, with Penn State being the most imminent forthcoming installation, sometime probably within the next 3 months. So in order to get as much a view of the sky as we can, we have these cake pan feeds just pointing directly on sky, so we get as much sky as we can. And each terminal is really its own separate instrument. They talk to each other post-detection for event coincidencing, but we're not doing any kind of interferometry with these. So each of them is designed to operate somewhat autonomously. So moving forward, what is the signal path for each of these devices? I have a bit of a diagram starting directly from the radio signal coming from the sky. It goes into our feed through our low noise amplifiers. These are the same ones used at DSA 110 and into our front end electronics enclosure. And we're an L-band survey, so our center frequency is 1.4 gigahertz. We've got 250 megahertz bandwidth, and we do our digitization on a snapboard with around 8.2 microsecond time intervals. That equates to around 1 gigabyte per second being transferred from the front end to some nearby server over either Ethernet or fiber, depending on how far you need to transfer it. So on the server side, we have a real-time detection pipeline. The first step of this is T0. This is handling all of the different data transferring. It also converts from voltage data to Stokes I, does some RFI mitigation, as well as burst injections. It also makes a copy of the incoming voltage data, shoves it into a 60-second ring buffer so that we have 1 minute to do all of our real-time analysis. Then it gives the Stokes I data over to T1. T1 is doing the first step of the burst detection. It's a custom implementation of Heimdall. And the output is something we're calling G-REX candidates of interest. These candidates have 4 main parameters: dispersion measure, signal to noise, time of arrival, and then the width. This is the boxcar width that's being convolved back in Heimdall. These candidates, and there's a lot of them generated, then go to T2, which is basically we do clustering with HDB scan to get refined candidates, and then again some specialized thresholding there to determine whether any of those are a potential burst. If there are any potential detections, that sends a trigger down to the ring buffer saying dump all of your contents to disk and we'll visually inspect stuff later. Also sends a trigger to T3. T3 then opens the saved voltage data file, makes an image of the burst, and it also is in charge of event coincidencing between different terminals. The images go to Slack for visual inspection, and we're also able to monitor the entire system over Grafana. So here's an example of what some of the output looks like. Over here on your left is basically a false positive on sky trigger because the RFI was kind of weird and not properly mitigated. So we got a trigger, but it isn't anything astrophysical. And then over on the right is an example for an injected burst. And of course, we keep track of our injections so we can ambiguate between something real and something synthetic. So we have metadata on top, signal to noise, dynamic spectrum, D dispersed to the DM found by Heimdall, and then of course some DM versus time plots. So how are we confident that we're actually seeing the sky? Well, we can look for two very bright signals. That's the hydrogen 1 line intensity from galactic neutral hydrogen, as well as the sun. Our beams are very wide, so estimating initial guesses of around 70-degree full width half max based on the stair 2 full width at half max. We can make some simulations of what we expect our response to the H1 line to be, as well as actual measurements. So on top in blue are the actual measured value for H1 line intensity, and then red is basically the solar continuum that I've subtracted from the spectrum for each of those measurements. Below that is a image of galactic hydrogen. This is taken from the Leon Argentine Bonn lab survey, and superimposed on that within this moving kind of region on the sky is a simulation of the section of sky being illuminated by our beam throughout one day within the full width at half max. And so in order to get simulations for what we expect the response of our terminal to the H1 line, I just integrate over the beam as it goes through the day. And I don't know if you can see it. It's supposed to be this dashed blue line, but it fits quite well to the actual measured data. And of course, you can see the spectrum over on the right, due to Doppler shifting, the center frequency sways around a little bit, as well as the actual line widening and thinning. So then the idea was, okay, we can make expectations of what the H1 line response shape is going to be over one day as a function of your beam size. So we can take actual measurements, compare that with a whole bunch of different expectations for different beam widths, and try to match them up to get a more accurate idea of what our beam size actually is. So over on the left, I have 23 days of data stacked on top of each other, as well as a range of simulated beams ranging from 50 degrees to 100 degrees full width at half max. And then just the RMS error between each day and each model shows a clear preference for full width at half max of around 65 degrees. If we go then to our center frequency at 1.4 gigahertz, we find that the expected field of view is approximately 4,600 square degrees. This is about 11% of the sky seen by a single terminal at any one time. And of course, from that, you can get an expectation of what your gain is. In order to get an idea of our sensitivity, we measure the system temperature for G-Rex terminal. This is with a Y factor test with some hot foam over the feed and a presumably cold sky. And we see a representative system temperature of about 36 Kelvin. So if you combine this with the gain gone from the field of view from before, as well as a signal to noise threshold of 10 to be able to claim a detection, say that our bandwidth is somewhat heavily impacted by RFI and a burst width of 1 millisecond, we get a minimum fluence of about 50 kilojansky milliseconds. All right, so now this is kind of for demonstration about how much of the sky are we actually illuminating with the 5 current beams plus 2 and maybe another forthcoming terminals. So the grayscale is just showing sensitivity to a certain section of sky, and this is a snapshot taken at a fortuitous time when all of our beams look very nice in galactic coordinates. But what's of maybe more interest are these contours showing regions of sky where 2 or more beams are above their full width at half max at any given time, and that is more useful for event coincidencing between multiple terminals. We can also integrate the beams, which are quite large, as they move through the galactic plane each day to get an idea of how much total exposure time we're getting for any particular sky coordinate. So minimum around 3 hours, maximum around 15 hours per day. And then I include also pulsars to get an idea of the galactic background. Magnetars is, of course, a source of interest, and specifically SGR 1935 is in purple there, which we're decently sensitive to. So if we take the on-sky time, as well as the sky coverage for both the STARE-2 project, as well as the G-REX terminal at Owens Valley, which has been on sky for about the last year, we can put some upper limits on the FRB event rate above our detection threshold. So the 95% limit is around 8.4 events per sky per year. But again, this is based only on sky coverage and exposure time, and so you're implicitly assuming an isotropic distribution, which for events above our threshold is probably not true. So what we're doing now is looking at refining these rate estimates by doing a kind of standard source counting where you take some distribution of sources. This is that N subscript D in galactic coordinates. And you're going to integrate through a whole bunch of parameter space. But what's really doing the heavy lifting here is this D max as a function of theta. Theta is some vector of parameters that describes the sensitivity of your terminal, how scattered a burst is if it comes from a specific direction, a specific distance. And it tells you how far in that direction can you see, how much of the population are you sensitive to. So the idea is to get this mean number of detections expected per terminal, combine them in a reasonable way to get a likelihood function, and use that to get some idea of these different parameters. So in review, we have 5 currently operating G-REX terminals, hopefully 2 or 3 coming online shortly. I've put up the individual terminal specs here, but I think the main ones of interest are that we are sensitive to burst widths down to 32 microseconds and up to a millisecond, and that each terminal is able to cover about 11% of sky anytime. Another point of interest is that G-REX is on sky all the time, doing this kind of all-sky survey, but there's a lot that you can do with the instrument in parallel with the burst search. There's some ideas to implement a separate backend for SETI techno searches, using the data collected with G-REX to develop RFI excision methods. And then if we implement it on G-REX, we can search down to lower dispersion measures. And then also developing machine learning-based burst detection methods using our data that we can run to maybe either replace or supplement T1 and T2 in our pipeline. All right, thank you.
All right, we've got time for a couple of questions. So, and first.
Hi, it's Dotan. You mentioned this Dmax, but if you can give some order of magnitude, like what's your horizon for like a typical FRB?
Sorry, what was that?
What is your horizon to like a typical FRB? Like to what distance can you?
Oh, yes. So we're, for a typical FRB luminosity, I think if we do the math, we're maybe definitely galactic, and for a really special event, maybe a very local extragalactic environment, but mostly we're just looking for galactic events.
Thank you.
So Mary's hand.
Oh, well, I have 2 questions, but they're very brief. Okay, hi, Marilyn Cruces here from UC Chile. So one question, the injections are all done in digital, or like you also have like some analog injections?
Right, yes. So the injections are done into the voltage data, and then
Okay.
so they remain in there in the voltage dumps.
And then the other question is, like, I guess there has been no detection even of pulsars or any galactic source. What about solar flares? Because the sun has been quite funky in the last 1 to 2 years.
Yes, so we haven't done too much searching for solar flares in the regular pipeline, just because we have a lower threshold on dispersion measure there.
Okay.
But we do see activity in the solar continuum where it will fluctuate in intensity.
Great. Well, let's thank Sash again.
Thank you.
And as always, you can ask him questions in the Slack. And our next talk is going to be from Seth Siegel, anticipated since Kendrick's talk this morning. So Seth, when you're ready, take it away.
Okay. Yeah, thank you to the organizers for the opportunity to be here and tell you all about CHORD. CHORD is a next generation radio interferometer that will be built at the Dominion Radio Astrophysical Observatory in British Columbia, Canada, right next to CHIME. It's going to build on the success of CHIME in the area of radio transients, but also make some changes to the design. As you can see, they look very different, to better enable the 21 centimeter intensity mapping and also open up some new science domains. So of course, I'm here on behalf of the CHORD collaboration. CHORD consists of a number of institutions throughout Canada, the United States, and Italy. And CHORD will consist of a compact core array of 512 6-meter diameter dishes located on a rectangular grid. This design enables fast algorithms for beamforming. It also has a high degree of redundancy, which we plan to use for precision calibration. CHORD will have 2 outriggers, each consisting of 64 6-meter diameter dishes. The CHORD outriggers will be located at the same place as 2 of 3 CHIME outriggers. So the Hat Creek Radio Observatory in Northern California and the Green Bank Observatory in West Virginia. This will provide baselines of more than 1,000 kilometers, which when combined with CHORD's ultra-wideband will enable us to localize radio transients to better than 50 milliarcsecond precision. We're planning to combine the first 48 dishes of the CHORD core array into a Pathfinder instrument, and we expect the Pathfinder to be operational late this year. So this is a picture of the first CHORD dish. It was assembled and installed early this year. The focus of each dish is outfitted with a dual polarization antenna with a system temperature of about 30 Kelvin and an aperture efficiency of 50%. So this gives us an SEFD of 12 Janskis. And one of the unique aspects of CHORD is this ultra wide band. So we're sensitive to frequencies from 300 to 1500 megahertz. That will give you a point spread function that varies by a factor of 5 from 17 to 3.5 arc minutes, and a field of view that similarly varies from 12 degrees to 2.5 degrees. So how does CHORD compare to CHIME? Well, CHORD has a factor of 3 larger bandwidth, twice the angular resolution, and a factor of 4 better sensitivity. CHORD is designed to mitigate the systematic errors currently limiting the CHIME 21 centimeter analysis. But the end result of that for transient studies is that CHORD will have a much simpler instrumental response, which should be easier to calibrate things like flux and polarization. And finally, thanks to a new GPU-based RFI excision and de-dispersion algorithm that Kendrick went over, our FRB search will be a factor of 10 times more powerful. But it does have a downside. So the field of view is much smaller than CHIME's. So you can think of the two as complementary. CHORD will carry out a shallow wide survey, whereas CHIME carries out a shallow wide survey, whereas CHORD will go deep and narrow. In terms of observing strategy, CHORD is drift scan. It relies on the Earth's rotation to move the sky across its field of view. And we can manually adjust the declinations this is pointed at using a power drill, as shown here. Welcome to precision cosmology. We can look at declinations between 20 and 80 degrees, and that opens up about 35% of the sky. So as the Earth rotates, we'll cover a strip at the declination that we're pointed at over a particular sidereal day. And this strip will be wider, much wider at the low frequencies compared to the high frequencies. So CHORD has a number of science objectives. Chief among these is detecting and precisely localizing tens of thousands of fast radio bursts, but it also aims to precisely measure the baryon acoustic oscillations in the distribution of neutral hydrogen using 21 centimeter intensity mapping. It will detect the largest sample of H1 galaxies in the local universe to date. We plan to use CHORD for detecting new pulsars and timing pulsars to aid in the detection of the stochastic gravitational wave background. And then its ultra-wideband makes it excellent for using Faraday rotation to measure synthesis. So Faraday rotation measures synthesis to study galactic and cosmic magnetism. So in terms of timeline, CHORD was proposed in 2020. It was fully funded by the Canadian Foundation for Innovation in 2021. In late 2022, we began construction on the core array. And looking ahead, we're planning to commission our 45-dish Pathfinder instrument in fall and winter of this year. If all goes well, the full 512-dish array and Outriggers will come online in fall 2027, and then we'll have a 5-year dedicated observing period. So some progress on the dish fabrication. We built a custom facility on site at the DRAO to fabricate the dishes. That's shown in the upper left photo. The dishes are made out of a fiberglass composite with a metal mesh embedded inside. And this technology is really being pioneered by the National Research Council of Canada. It allows us to build these dishes at sub-millimeter precision for relatively low cost and relatively quickly. When we reach a maximum production capacity, we'll be building 1.5 dishes at each business day. Once the dish is complete, it's loaded into a truck and driven a short distance to the site and then installed on these pile foundations. In the lower right, you can see 8 of the 9 dishes that we have fabricated and installed so far. So we're using an FX-style correlator. The digitization and channelization of the 512 inputs is carried out by the F engine, which is being developed here at McGill. It consists of 128 of these FPGA RFSoC boards. The data is then routed through a network switch to a GPU-based correlator and beamformer. This is being developed primarily by the University of Toronto and Perimeter Institute. This stage runs 128 NVIDIA A40 GPUs. You can see the GPUs in this photo on the right. Currently, they're sitting in a DRAO high bay waiting to be installed. We heard from Kendrick this morning about a new GPU-based FRB search algorithm. Roughly, the computational cost of the D-dispersion goes as the data rate, which I'm defining as the number of beams times the number of frequencies divided by the sampling time. And this new code can handle 10 gigasamples per GPU. We have 16 GPUs total, pictured on the right. So we'll have a data rate of 160 gig samples per second. And just comparing this to some other experiments, you can see that we're a factor of 10 times larger data rate than CHIME and even a factor of 2 larger than SK-MID. So the FRB search backend has a number of additional features. So most of these are being driven by the ultra-wideband. So the interchannel dispersion delay scales as frequency to the -3rd. This means that we'll have a 125 factor increase in the dispersion delay between 1500 and 300 megahertz. So to deal with this, we want to narrow our frequency channels as we go to lower frequencies. And we do that by increasing the channelization by a factor of 2 at these fixed boundaries. We're going to have a 100-second baseband buffer, which will be about 85-second effective length after you account for lag and other memory considerations. But that's going to comfortably fit FRBs with DM less than 2000. For higher DM FRBs, we're implementing early baseband triggers. So this shows the arrival time as a function of frequency for a DM 3000 event. And you can see that the lower 10% of our band accounts for 50% of our dispersion delay. So for this event, if we waited till the lowest frequency arrived, we would miss the majority of the event. So we'll implement an early baseband trigger where if this burst has enough signal to noise to be detected at 410 megahertz, then we would send a signal to a trigger to drop the baseband buffer at that point, so we capture this full burst. This will only miss the very dimmest broadband events that require the full band to get the full signal's noise. The FRB search will have arbitrary formed beam locations. I'm showing here the instrument response, which I'm defining as the product of the primary beam and the synthesized beam at the lower and upper edge of our band. And you can see that at large angular offsets, many formed beams have negligible response at the upper frequencies due to the narrowing of the primary beam. And then the other effect is if you zoom in on the central degree, you'll see that the formed beams are very tightly packed at low frequencies, whereas they're reasonably filling the primary beam at high frequencies. And that's just because the synthesized beams also scale with frequency. So even if an FRB is broadband, the instrumental response will introduce some non-negligible spectral dependence over a pretty large fraction of the sky. So to deal with that, we're performing multiple subband searches. And this is a strategy led by Matteo Trudeau at INAF. And this plot, each color shows the frequency extent of a different subband that we would search. These are uniformly spaced in new frequencies to the -2, down to a minimum width of 100 megahertz. And this approach is simple to implement with the existing tree-style dedispersion algorithm, and has been shown to significantly boost detection rates in simulations. But it's an open question how sensitive these subbands will be to narrowband RFI. So we have a great deal of flexibility, and we need to figure out how to properly, with the search, and we need to figure out how to properly use that flexibility to maximize our scientific yield. So in order to do this, we've implemented a global optimizer. So this takes as inputs a number of search parameters, things like the sampling time, the upchannelization boundaries, the number of formed beams, the location of formed beams in the sky. You feed it a population model for your FRBs, and then also an instrument model. And it performs a multi-dimensional integral over frequency, sky, and burst properties to estimate the detection rate for a given set of search parameters. And then once you have this framework, you can use a nonlinear optimizer to optimize your search parameters to maximize the number of FRBs detected, given some fixed computational cost. And you don't have to use this particular objective function. Whatever type of FRB you're interested in, you can come up with a quantitative measure of success in that particular science and plug it into here and optimize for that. So this is optimizing CHORD. So we find the following parameters: optimize the CHORD search, 1 millisecond sampling time, 7,000 beams on the sky, and 20,000 frequency channels. This, of course, assumes the population as measured by CHIME FRB catalog 1. And you can just see changing some of the objective functions in the upper plots. So on the left, I'm showing the upchannelization as a function of frequency, and the beam distribution on the left, and the beam distribution as a function of angular separation on the right. And if you wanted to optimize for the high DM events, you would, of course, use higher upchannelization factors and fewer beams on the sky, which is shown going from blue to green. This is the number of FRBs detected above a given redshift for 1 year of observation for CHORD, the high DM optimized CHORD, and CHIME. And you can see that CHORD will have a significantly larger horizon, detecting events out to redshift 3 to 4. And you can modify that slightly by optimizing the search in different ways. If you want to lower the overall detection rate in favor of having a better chance of detecting high DM bursts, you can do that to some extent. And then my final slide, I'll just show the detection rate. This is the detection rate as a function of angular position on the sky. CHIME is on the left and CHORD is on the right. And this just shows the sort of shallow versus deep survey strategy. The majority of CHORD FRBs will be detected within 2.5 degrees of where it's pointed. And if you integrate this image over the full sky, you get CHORD detecting 10 to 20 FRBs per day with better than 50 milli-arcsecond localization. So here's just comparing the redshift distribution, assuming the population model as constrained in Shin et al. Fit to the CHIME FRB catalog 1. Okay, and I'll maybe leave my summary slide up and take any questions. Thank you.
I think I saw Laura's hand first.
Hi, this is Laura Spitler from MPIFR. Very interesting talk. So I have a question about your data publication policy. We heard from DSA 2000 that they're committing to publishing all of their data on the public archive immediately, including rapid FRB alerts. Does CHORD already have plans for how they're going to disseminate their discoveries?
I don't think we have any plans. We have not discussed that info yet. I imagine it will be sort of inherited somewhat from CHIME FRB. So VOE events and in terms of publication of catalog, that hasn't been decided yet.
Yeah, Martin Topinka from Cagliari, Italy. I wonder, like, when you mentioned that 100-second buffer, so which is like designed for to be able to capture the very like large DM things, would it be somehow possible to like improve the interplay for like multi-wavelength like counterparts, like a search, like to listen to the triggers from other like imagine like in gamma ray bursts they have the GCN networks, which is not only like by sending emails, by directly like you're listening to the stream of the like immediate event, so you can imply this into the like the actor picker or action picker, like to save it even if there is something which is could be rejected, but since it's 100 seconds, it's more or less the time that the signal comes from the, let's say, the satellites to the ground stations and distributes around. So it's usually like 1 minute is what usually in optical observatories do for a rapid follow-up. So this could be option.
It's an interesting idea. I think extending the in-memory baseband buffer is not feasible, so we're sort of limited to 100 seconds. And I guess it's just a question of the lag between these multi-wavelength counterparts and when we can find out. I think we are planning on taking triggers from CHIME, so taking them from some other instrument would be easy. And I think Matt mentioned using a different type of buffer from solid state drives, and maybe we can discuss that in the future discussion section.
All right, let's thank Seth again. And as always, discussion can be continued on Slack.
I'm able to do this with my hat is the question. Hello, hello. You guys hear me okay? Sweet.
Great. So now we're going to hear about CHIME FRB Outriggers from Mattias Lazda. So take it away.
Awesome. Thank you. Thank you. Oh, hello, everyone. My name is Mattias Lazda. I am a second-year PhD student at the University of Toronto, hopefully a candidate if I pass my qual next week. So fingers crossed. And I'm super excited to be here. I've been working on FRBs for the past 4 years in the Outriggers, but it's the first time I've been able to actually come to one of these conferences in person, so it's been great to see everyone. And before I even start, I think there's the reason that these Outriggers are anything beyond just the concept of a plan is largely because, or it's basically all because of the Gordon and Betty Moore Foundation, which without their financial support, we wouldn't be at the point that we are today and do the science that we're aiming to do and have been able to do already. So I know that a lot of you are probably wondering what the Outriggers have been up to over the past couple of years. And there's probably one thing that you're wondering is, are they all online? Are they localizing FRBs? And what is the localization precision of these FRBs? So I'm happy to report that the Outriggers are definitely all online now. And the rate at which we're currently localizing FRBs is on the order of 5 to 10 FRBs per week. And the typical localization uncertainty that you should expect from these localizations is roughly 60% of them are at the 50 to 100 millisecond level. This is 1 sigma localization regions. And then the remaining are lower signal to noise events that are not localized to such high precision, but still getting better than 300 milliarcseconds. So if that's what you're interested in, those are the numbers. And then the rest of my talk is kind of just going to give you a brief overview of how we got to this point of where we are today. So stepping back, maybe just to give a broad overview of where we are with the Outriggers. In 2022, we had the first Outrigger that completed its construction in the summer of 2022. I spent the summer out there doing some analog deployments as well. In spring, it then entered its commissioning phase, and then in the spring, we finished construction of the second Outrigger, which is located at the Green Bank Observatory, forming the longest baseline with CHIME and gives us the best angular resolution. In the summer, about a year after commissioning KKO, or the first Outrigger, we started to localize FRBs on the order of about an arcsecond along the direction of the baseline, so a 1D localization preferential to the east-west direction. And then fast forward a couple months to spring of 2024, and then GBO finished its commissioning phase and also started to localize along the east-west direction. Since they're roughly collinear, it kind of just improved on the localization accuracy of KKO by a couple orders of magnitude. And finally, after many, many months and many years actually at this point of dealing with permitting and dealing with the challenges of installing a new telescope at site, we finally turned on the telescope for the first time in early winter this year. We had various phases of analog and digital deployments, which I'll go into in a little bit afterwards. But in the early winter, we finally turned on Hat Creek. Since then, we've started to see some of our initial science results come out. So just to highlight a couple of these that have happened over the past 6 months, we had Vishwangi and a companion paper led by Taranay, where they had localized a repeating fast radio burst, offset, and likely in a globular cluster origin. And this was all used using the first Outrigger. We had Calvin this morning talk about using the local universe of fast radio bursts, also with a KKO Outrigger. At this point, we then made just an interjection that yes, we finished construction early winter, but since we've done this we've done this 2 times already. We're now kind of become experts at commissioning these radio telescopes. We shortened the time at which it took for us to get just on sky. We localized our first pulsar within a week of turning on the instrument. And it started to reach the point where we were confident that we could start localizing FRBs with Hat Creek and then retroactively going back and improving the astrometry as we went on. Since then, we've had work that Vic has been leading and doing cross-match with a KKO sample of historical transients and historical supernovae. And then Alice published the first GBO localization, which was being observed at the same time as Swift. And then, of course, the most recent result was that we had the RB float, which was the first full array localization. So as you can see, it's been very, very, in the span of 6 months, they started to very much exponentially grow in terms of the science that we're able to do, and it's only going to get more messy or I guess more enjoyable in the future. So at this point, a lot of the effort that has gone into getting these Outriggers working is just the emphasis of this slide is very much to highlight that this effort is largely powered by the graduate and postdoc group that maintains and is able to not only commission these instruments, but also maintain them on a daily basis to make sure that they're running in stable operations so that we can continuously keep producing more FRBs and getting them. It's not an easy task, but it's something that we all love to do. Well, at least some of us love to do. I love to do it, but it's great. And of course, this is only a subset of the people working on the Outriggers. Basically, everyone has contributed in some effort. And maybe this is kind of my, especially what I love to do. It's focusing on how do we actually turn a hunk of metal into something that can localize FRBs. And the main method, or this is just kind of a snapshot into what it's like. So especially at Hat Creek, which is a very remote site at the Hat Creek Radio Observatory, we kind of have these deployment phases. So on the left, you can see, on the left, kind of a typical, this is what our focal line looks like, where we install all of our antennas, cable up the system. And yes, I know the cabling is probably not the most pretty, but once you spend 2 weeks out in the hot California sun, you start to stop caring, and you just plug it into the wall, maybe to the chagrin of other members. But yeah, we're just happy to have an instrument that's able to localize FRBs, and we go back every once in a while and try to clean it up a bit more. And another thing too is that when we lead this with primarily graduate students, and especially the digital deployment was all graduate students, we get very, we're hardworking and sometimes very, very hardworking, such that especially when the only time that you can find shade in Northern California is in the trunk of a car and Kaylin is sleeping. Since then, beyond just analog and digital deployments, a lot of the bulk effort goes into characterizing the sensitivity of these Outriggers, so making sure that they're performing to spec. So this is currently work that's being done by German, who was a previous undergrad at U of T, but is now starting his PhD. And then on to the right is kind of an effort. There was a broad period of roughly 8 months of low sensitivity at Greenbank. And this ended up being due to poor calibration solutions, but having saved visibilities over the course as we kind of hoard our data, we were able to retroactively go back and improve the calibration of these. And this is an effort that's being led by Rachel, and we should be able to recover on the order of 60 FRBs on the GBO baseline. A big bulk of the effort now is going towards characterizing our astrometry, and this is a monumental effort that's being led by Shion and other members of the collaboration as well. And just kind of to highlight the method that we do this is largely twofold. We test our pipelines on known sources that have known VLBI astrometries, whether they be pulsars or also VLBI continuum calibrators. So just to point some numbers here, these lines are kind of the typical localization uncertainties on these sources that we've targeted. And on the GBO baseline, we're comfortably hitting 50 milliarc seconds once we get above signal to noise of 20 in cross correlation. And on the High Creek baseline, given the slightly shorter baseline, we're getting closer to 100, but we're working towards improving this over the course of the following years. And just kind of to reiterate this point, we're getting roughly 3 to 6 FRBs per week that fall within this regime, but we're still able to, as long as the signal to noise is sufficiently high, we can still localize FRBs that fall in the lower, just with arguably larger uncertainties. And not only do we localize known pulsars and VLBI sources, but whenever we get a localization or a detection of a repeater that has an EVN position, we cross-match with the EVN localizations. So this is just an example showing a single burst localization of R3, and with the EVN star highlighted just smack dab within our localization region. So kind of gives you a sense of scale of what the typical localization region of an average FRB would look like for at the present time. So that's everything that we've been up to over the past year and our past couple of years. But the question is, are we done? It seems not entirely. And of course, all these talks before me are talking about these 20 FRBs, 30 FRBs per day. And I'm just, we're getting there. Well, we're not going to get there, but maybe not at that level, but we're working towards improving so that these future generations can push to that limit. And kind of the major effort that's currently being undertaken by Aaron Perlman and Andre Renard is the ability to employ or deploy tracking beams at each of the Outrigger sites. The main benefit of this is that we've noticed that in a subset of our localizations, about 30% were limited by the signal to noise of the calibrator, both due to just scarcity of calibrators, but that's only because of the low integration time that we have in our typical voltage data. Where in this case, the tracking beams will both reduce the data rate and provide a calibrator that's as close to the target as possible on sky, boosting the signal to noise of the calibrator and also being able to track the ionosphere variations and kind of higher precision and reducing or improving our ability to localize more efficiently. So this is just going to briefly over the past, this is just an overview of what's kind of been going on. I would say at this point, the Outriggers are largely all commissioned. There's still work in progress to fully characterize their system, the system sensitivity. And this is we'll have companions similar to the papers that we did with KKO, where we showed the response of the system and the behavior of the system. We'll have similar papers for GPO and Hat Creek. And we're also going to be having a dedicated astrometry paper that is being led by Shion in order to just showcase our ability in terms of for various, whether it be on bandwidth or in any case, a dedicated astrometry paper that if you're interested in learning more about that, feel free to ask. Once we finish this, then we would say that commissioning is largely complete. And then the next phase is going to enter the optimizing our ability to localize FRBs consistently and push our systematic noise floor as low as we possibly can. So I think I will leave this as my summary slide, just kind of highlighting the typical rates at which we're expecting. And I'll take any questions if there's any.
Yeah, any questions for Mattias? Yep.
Max, I'm an incoming PhD student at McGill. Are there any secondary science goals for the Outriggers?
Yeah, we're cooking up some stuff. There's current plans that it's whether or not we can get we have one of them. I'll just mention one that I'm interested in, and we're trying to do an ad hoc as much as we can, do a VLBI imaging array. It's not necessarily the most sophisticated. It's definitely not the best for it. But especially there's work that Xion led early on to establish kind of a calibrated grid of VLBI targets that could be used for future generation observatories. And we're going to try to expand on that and try to get more representative flux density measurements so that future generation observatories could have access to all these calibrators.
Yeah, Adam Dong from NRAO. Just to follow up with everything. One of where a very secondary science goal would be we're trying to do astrometry for pulsars. So there's a little group of us now that's very interested in this. So the hope, the stretch goal is parallaxes for northern hemisphere pulsars. And if we can do what we think we can do, we can get a lot of them of daily coverage as well.
And this is Robert Main, the chair. Also, we can resolve scattering screens, map galactic plasma. That's my pet idea to use the Outriggers for. Any last question here or online?
Or maybe it's not a question, but a comment with the localization. And it's something that I haven't heard here the entire week, which surprised me. That if you have a good localization and maybe you can see more FRBs coming from global clusters, like was that one peculiar case. And if we make a connection between magnetars and FRBs, it will actually like be a proof that maybe of a different like creation channel of magnetars, not only like, so it's like a impact on different fields a little bit. Sorry? Sorry, Martin Topinka from Cagliari, Italy, enough.
Yeah, that's a great point. And I think, I guess we'll have to see, we're still processing through the localizations and doing the optical follow-up led by in conjunction with the F4 team. So hopefully we find some nice samples that point to these different ideas.
Great, well, let's thank Mattias again. Okay, and we're going to hear from Tomás Cassanelli about charts. And Tomás, take it away.
Yeah, thanks. Can you hear me well? Yeah, I am Tomás from University of Chile, and thank you for the organizers for having me here. I'll be talking today about this project, which we call CHARTS, which is the Canadian-Chilean array for your transient styles. Yeah, so of course, I'm presenting on behalf of my students, co-Is as well. We're working with the University of Toronto and University of Chile, and a bunch of students, including graduate students as well, from both institutions as well as postdocs. Here on the figure, on the right side, you have a picture of nice optical telescope, but in the bottom of it, we have these few dipoles or patch antennas that we're using right now. I don't need to convince you that FRBs are cool, so I'm going to skip this. Yeah, so FRB detection, how we detect FRBs? We need first a large collector, as you know. So that means increasing our sensitivity. So that is taking the flux of a source and transforming that to milliwatts or Kelvin. We need also a huge field of view that will increase our chances of detecting FRBs. But also we'd like to have a small angular resolution. That means localizations of these events. And that's why CHIME is a great tool for this, an interferometer. On the other hand, we have the FRB detection rate. The FRB detection rate scales to the bandwidth to 0.75, but also the number of antennas in the case of an aperture array to 1.5. So the bandwidth at the end is not that as heavily penalized as the number of antennas that you have in your array. That's something to keep in mind. As you know as well, most FRB detectors are located in the northern hemisphere of the world. So that means that there's a lack of detections in the south. Roughly less than 20% of one of FRBs are located in the south. Don't quote these numbers. I haven't added any from the new results that we have shown in this conference. And also less than 4% of repeating FRBs have been found on southern latitudes. So that's another reason why we should focusing on building something in the south. So this is how CHARTS came to be alive. It's going to be located in South America, in Chile. It's going to be a specific transient radio array. That means that most of our parameters, the sky, all the digitizers, all the things that we need to optimize the rate detection of FRBs will be highly specific for this purpose. Since also we're all going to be observing in the south, that means like a large portion of every day we're going to be observing the galactic center. That gives us also another motivation, which is not only FRBs, but also a side target, which are magnetars or other exotic galactic event. And of course, since we are located in Chile, there's a wide variety of other observatories, such as optical, millimeter wavelengths, and so on. So we're going to be actively collaborating with them. So yeah, this is CHARTS. So CHARTS will be this low-cost aperture array. To accomplish this low cost, we're going to be employing something that we called, has been used several years already in telecommunications, which is called multiplexing. And as well, we're going to be using a differential RF architecture. We're also be using similar as what Seth mentioned in the core talk, using this RFSoC or radio frequency system on chip, but the cheaper version for our array. And of course, we're going to prioritize the number of antennas rather than the bandwidth itself. So we're going to reduce the bandwidth a bit and increase the number of antennas for our sensitivity. So this is the array distribution that we are thinking of, possibly a sunflower. We haven't put this on stone yet, but it's something of the applications that we could have. And as you know, an aperture array scales the effective area of it, scales the number of antennas, the number of beams, and also to the lambda square. We're going to be having 256 elements. Each of these elements will have, these patch antennas will have a beam width of roughly 90 degrees. And we're going to be having a field of view of 1,000 square degrees operating in modest bandwidth of 200 megahertz, from 300 to 500 megahertz. With this configuration, we expect, this is a positive forecast, roughly 100 FRBs per year. Why did we choose this passband of 300 to 500 megahertz? Basically because we know that from previous observations, catalogs, we know that FRBs tend to be a bit higher intensity around the 400 megahertz. So that's why we chose that section there. We're going to be focusing on these 4 main points: emission mechanism, progenitors, magnetar bursts, or any other exotic event from the galaxy, and as well new repeating FRBs, which are one of the most exciting things that we could do with multi-frequency observations. So again, we're going to be optimized for bright and nearby FRBs, and we're going to be operating this band of 300 to 500 megahertz. CHARTS will be located in latitude -33 near the city of Santiago de Chile, at the outskirts of it. And you can see here the location is this star. I don't know if you can see my cursor, right? Yeah, this star. And also, you can see here other telescopes, that large telescope, optical, millimeter, that have the same field of view. CHARTS will be located in the park called Laguna Carén, which is at the outskirts, again, of Santiago de Chile, and that looks something like this. On figure A, we have the park, which is isolated by several gates to the public, so we don't want to be worried too much about the RFI environment for cell phones. It's sort of shielded by these mountains that you see in the background. And yeah, it's a very isolated, great place to have the array. This is an aerial view of the location. We're going to be using roughly 20 by 20 meters. This is dry vegetation that happened in the summer. And then actually a few months ago, we started to put some grounds there so we can start putting our antennas. This is going to happen, a big deployment in January of 2026. Over there already is the container that we're going to be using to host our electronics. So the CHARTS field of view will look something like this. As I said, will be an 8,000 square degree observatory will going to be, what I'm talking about here is the blue circle corresponds to charts. On the cyan color corresponds to burst project, and on red corresponds to the CHIME FRB far side lobe. And as you can see, our project, our aim of our project is more than complement the existing catalog and the existing field of view of other projects that are currently existing worldwide. Yeah. Our antenna will be, it's already in several iterations of development. It looks something like this. It's a patch antenna, as you can see, differential. And with differential, I mean that we're working outside the paradigm of the 50 ohms impedance for the antenna. It'll have a 90-degree field of view and will make the system to operate in a system temperature below the 50 Kelvin. This antenna has been developed by postdoc Albert at U of T. And you can see here that one of the cool things that it has that incorporated the LNA within the antenna itself. So we're going to be reducing a lot of the temperature there. This antenna, again, has been built at the University of Toronto and Universidad de Chile. We've been testing it. We've been building, right, the structure of it. We 3D printed this, the students did, as well as the mesh that we have here. We built a sort of a structure to isolate as well and weatherproof the LNA. And it's been working great so far. On the other hand, we have this radio frequency chain. So on the left-hand side, we have the antennas. So we have 256 elements, each of these antennas. So our, as I said earlier, we're going to be employing this multiplexing technique. And that means that every 8 antennas, we're going to stack them together, not combine the voltages, but stack them together one side by the other. So each of these has 200 megahertz. So then after this system, which we call FDM or the multiplexer, will have a bandwidth total of 300 to 2.3 gigahertz. And that's what's going to be digitized within this RFSoC or FPGA. One of these FPGAs has the capabilities of 5 gigasamples per second. So we're going to be actually digitizing 8 antennas per ADC. So that means 32 antennas per a single one of these FPGAs. So that's very convenient for us. To complete the entire array, we'll need 8 FPGAs. And with 8 FPGAs, we'll have 256 elements of the radio interferometer. So that's the key, one of the key concepts of this array is this FDM or the frequency division multiplexer. And this is the RFSoC model that we're using, which is the a smaller version of it, even has some academic discount. This frequency division multiplexer is one of the things that took most of our time. It's been almost 2 years since my graduate student, Sebastian, is about to graduate now. It looks something like this right now. It's differential. That means it will take something that is not from the 50 ohm classical impedance. And it's going to, again, take this 8 antennas and then combine them into a single one. We've been testing this for a while already. We're in the final iteration of it. And to make it more fun and to include, right, the to reduce the cost of the overall array, what we're going to do is using Ethernet cables rather than the standard SMA or the standard coaxial cables. So that way, we're going to be reducing the cost of the overall array. This is what it looks like outside. This was a few days ago only. Sorry about the mess, like there's a lot of stuff going on at the moment. And yeah, we've been simulating this as well. Simulations have shown really good results, and that's Sebastian, my student, that has been working on this. I can talk to you a bit about this later if you want in the coffee. Also, we have the F-engine. F-engine will be entirely done in these FPGAs. The F-engine is being developed by my student, Bruno. And similarly as other projects, we're going to have a 4x4 bit structure, a PFP, Fourier transform, right? The entire spectrum of the 300 to the 2.4 gigahertz. We're also going to be generating the LO tones that we need as well for this FDM, since it's very similar to a heterodyne receiver. And as well, we're going to be applying the DMAPs, that is splitting back again the antennas to the original frequencies that we needed. The FX architecture is very similar to what Burst or CHIME FRB has, but with the exception of that we'll be having 8 of these RFSoC then we're going to split the band in 4 and feed it to GPUs. And those GPUs will be consumer GPUs, so in order to reduce the cost of the overall array again. So very similar architecture, with the exception of that the digitization, the PFP, and the DMAX will be done within these RFSoC models. So this project is being led by my student Gonzalo, and here we have one of the consumer GPUs that we have already in the lab and being tested at the moment. So this is the preliminary prototype that we have next to the astronomy department. We have 8 antennas currently working through the FDM, through this multiplexer. So we're taking the signal from these 8 antennas, feeding it to the FDM, and then we digitize them with this F engine that Bruno developed. And we have the first results of the spectra. I mean, it doesn't look that fancy, so don't be surprised, but we have still a few things to debug here, but currently we are capable of making this FDM work, so saving tons of money in the digitization of the process. So it's something really exciting that's going to happen in the next a few months. These are the parameters, and well, charts is a modest instrument. It will have great impact, will be built entirely by a university level, so students and profs, will be optimized for the rate and cost. That is how we're going to optimize in cost, is by 4 things. Optimize the antenna design, the FDM using this multiplexer, a differential RF, so we won't be using the classical 50 ohm cables, and we're going to be using consumer GPUs. And in January 2026, we plan to have 32 of these antennas in Laguna Carén, the final site. And with that, thanks. And these are my sponsors over here as well. We're working with the University of Toronto, University of Chile in a very collaborative group. And I'll take any questions.
All right. Questions for Tomás? I saw Mattias first.
Hi, this is Mattias from University of Toronto. I was just curious, are there current plans for establishing kind of outrigger stations at all? Is that in the works?
Yeah, so that's definitely what I've been planning to do as well. We have another location, a potential location in the south of Chile. We've also been contacting as well in contact with Liam Connor on CHASM as well, and trying to collaborate as well. Yeah, it's something that we are seeing. Yeah.
Hi, it's Marcus Lower from Swinburne University. So at these kind of frequencies, the scatter broadening timescale for the galactics into magnetars is like many, many seconds. So how are you planning to find those bursts if it does emit FRB-like emission?
So as what we have is like, are you asking about the computational power? Because we have 5.
No, I mean like, can you actually see second-long duration bursts?
Well, first of all, we're operating between the 400 to 500 megahertz as well. So we know that CHIME has detected thousands of them, right? And going below, we're going to actually increase the number of channels when we search, right? We're going to increase that channelization incoherent to search for the bursts, a bit more than CHIME, what CHIME does in the current band.
Okay, I think we can talk later.
Yeah.
All right. One more question, and the next speaker can start setting up.
Hello, I'm Sujay from Asia. Thanks a lot for the really nice talk, and I think it will be an amazing telescope to cover the wide field of view, wide field in southern hemisphere. I have 2 minor questions, and the first one is that how's the RFI situation at the site, and the second one is that whether you're considering to put radome for your antennas for prevent any damage, because you have a planar design. And I'm wondering whether there might be some damage if you keep without radome or something.
Yeah, that's first the question about the antenna. That's definitely something that we're investigating since these antennas are going to be outside in the heat. Actually, near Santiago, it rains only like a few times per year. It's not much of a problem. There's no many animals as well. So the only thing that could happen is like basically the heat that could potentially melt the antenna itself. So we're testing it, putting it outside, so we see how it behaves during this year, for example. That's something that we're investigating. And the first question was?
The RFI situation.
Yeah, the RFI situation. Yeah, so I have a few I knew this question was going to happen. So have it some. Oh yeah, that's it. So it looks better. So this over here corresponds to the RFI situation in the city, and this over here corresponds to RFI situation in Laguna Karen, which is a bit better. Yeah.
Thank you.
Yeah.
All right, let's thank Tomás again.
Hello. Yep. You can hear me? Yes. I need to load up your slides. Thanks, Mason.
All right, so following Sujay's talk this morning, we're going to hear a little bit more about the slow search. This will be a lightning talk from Jeff Huang, and take it away.
Yeah. Hi, I'm Jeff. I'm a PhD student here at McGill University, and I'll just be giving another quick update on the current status of CHIME slow. Okay, so as you heard from Sujay's talk earlier today, CHIME slow is CHIME's dedicated slow transient search, a single pulse search, looking for transients between a few tens of milliseconds to up to a few seconds. Since I don't have too much time, I'll refer you back to Sujay's talk this morning for a bit more details. So I'm happy to say that as of about 2 weeks ago, CHIME slow is now on Sky and with pseudo real-time processing, although at a bit limited capacity. So right now we're only searching on a third of CHIME FRB's field of view and with lower sensitivity. Part of this lower sensitivity is due to some data stream and quality issues that I think Sujay briefly touched on. And then another one is kind of just due to the wealth of false positives we're getting. So on the right here is kind of a plot of beam row as a function of time of our daily candidates. And as you can see, kind of evenly distributed throughout, there's tons of data points, which are kind of all of our false positives. But some of these overdensity regions you can see are the transits of bright pulsars. So it's good to see that we're still able to detect astrophysical signals. On the note of false positives, these mostly manifest in the form of RFI, both broadband and narrowband, and also more importantly, in the form of red noise. So red noise, for those who don't know, is this kind of long baseline variation that occurs over time. And this becomes increasingly problematic as we go to slower and slower timescales, especially when we begin to do single pulse searches on seconds timescales. And this is kind of demonstrated on the left. So one way we're trying to get around this is with something called incoherent beam subtraction. So this is as simple as just taking our beam, taking the average spectra of some of the neighboring beams, which ideally should share the same red noise and RFI profile, and then simply subtracting it. And this GIF is just on the right is what I made of the before and after. And you can see just with such a simple operation, there's such a dramatic decrease in RFI and red noise. As you heard from Daniele's talk earlier this week, CHIME slow was kind of the one to redetect this known pulsar, which unfortunately ended up being associated with the sub-second periodicity FRB. Although this was quite unfortunate news for CHIME FRB, this was pretty good news for CHIME slow. So the reason this was pretty good news for CHIME slow is because of this kind of, I'll come back to it. You can take a picture after, Jason. Because of this particular FRB pulsar, which is extremely highly scattered with many of its pulses stacked on top of each other, this the DM signal to noise maximizing DM is actually ended up being 50 DM units off. So we detected this as a single 2-second wide pulse. So although this isn't necessarily a new source like a new LPT and instead a known source, it's good to see that we can actually detect things that look like this because this is exactly the type of thing we want to see in the future. So hopefully, as we begin to scale up in the coming weeks and months and fix some of our issues, we can find more and more of these slow transients. Yeah, that's about it.
Okay, 1 or 2 questions for Jeff. Let's see.
Hey, nice talk.
Regarding red noise, there's quite a bit of machinery and tricks that it's not so easy to find in books on how to detect things in the presence of red noise. I would be happy to talk to you further later to...
Yeah, that sounds great. Yeah.
All right. If there's no other questions, let's thank Jeff again. And then we'll just take a moment to set up the final talk, which I believe is remote.
Go ahead and share your screen. Yep, we can see your screen, though you're still muted. Paducci, could you unmute? We can't hear you from here.
Okay. Can you hear me now?
Yes.
Okay.
All right. So whenever you're ready, you can take it away.
Yeah. So I'm ready now. Hello, everyone. I'm Vidushi. I'm postdoc in GCN team. So we are happy to announce the collaboration between CHIME FRB and GCN notices. So there will be announcement soon. So we will have new CHIME FRB notices through GCN system. And thanks to CHIME team and Tomás especially. So to cover up everyone, so GCN, which is General Coordinate Network, is a platform facilitated by NASA for distributing the transient alert information between ground and space-based observatory and thousands of astronomers worldwide. So we have two data products, GCN notices and GCN circular. Most of you FRB circulars are already there through circulars, and many people are aware of circulars mostly. Whereas notices is another product which is by machine, and on the left side example of notice is shown and is read by machine, and it has predefined format. So we can have like multiple CHIME FRB notices, retraction, detection, any through this GCN notice system soon. So GCN has been around since 30 years and scientific landscape has changed a lot. So it was initially for GRB community, then it evolved to the community observing the gravitational waves, high energy neutrinos, and the transients such as SGR, TDE. So even the technology landscape has changed a lot. There are better ways to serialize this astronomical data, especially Vera Rubin, which is online this month, is using state-of-art of technology for streaming their alert Patchy Kafka. So the new GCN system is also built on this Patchy Kafka. And here the GCN classic notices as producers are shown, which includes mostly high energy observatories, LIGO Virgo Kagra GW detector, and the Ice Cube. So we are transitioning to new notices, which is JSON based, and these new notices, we welcome all other transient community as well. So here's the step-by-step guide for producer are shown on the left, which is available over GCN website. The new notices will have a format of JSON as well as VO event are possible with it. So you can draft and design your own schema for this. Here the list of new notice producers as JSON format are shown. So these are the existing ones: Einstein, Guano, Ice Cube, GW follow-up. Some of our onboarding: Swarm, SK, KM3net, Fermi, and the CHIME FRB, which is already we have passed from test site. It will be in production within a few days. And there are other missions which are in the discussion of coming to these GCN notices. So these GCN new notices have unified schema, which is based on set of core schema built in with JSON format. It has consistent name and units. For each observatory, one can define the specific field as well. Here, as example of CHIME FRB is shown. On the left, schema is shown, and on the right, example of CHIME FRB, notice how it would look like, is shown. So this was still the producer side. Now from the user or consumer side, how you can stream these GCN notices using Python. So you can go to gcn.nasa.gov and then you can start streaming new GCN notices, even the classic one as well. So you can sign in, sign up, and you can choose your specific